Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Night after night, for billions of years, they have watched from the darkness. Moons, those pale, silent companions, have hung in the sky over every epoch of Earth's history. Long before any human drew breath, our moon cast its gentle light and stark shadows across primordial oceans and nascent continents. It lit the way for the first creatures that crawled onto land under its silvery glow. It has been a witness to all of our story. Imagine a night 100 million years ago, when the moon's pale disk shone down on primeval forests and the backs of dinosaurs. Those ancient giants cast shadows by lunar light among the ferns, unaware that the same moon would later glow upon early humans building fires on the savannah. The moon looked down on all of them, unchanged as ages passed. Through extinctions and renewals, through the drift of continents and the rise of consciousness, it kept hanging in the sky. By the time our species arrived, the moon was a familiar beacon overhead. It saw every ritual dance in its honor, every lover's whisper under its radiance, every explorer who dared to reach for it. In the stillness of midnight, the moon looms as a quiet guardian. Its face, scarred by ancient craters, glows with a cold fire, illuminating the night but never speaking a word. Yet in its silence, it has shaped the rhythms of life. The tides rise and fall to its tug, a planetary heartbeat set to the moon's pulse. In its waxing and waning, humans have seen a mirror of time's cycles, growth and decay, birth and rebirth. Its cool light has guided travelers, stirred the imagination of poets, and provoked the curiosity of scientists. It is our closest celestial neighbor, and for much of human existence, it was the most mysterious object we knew. But the moon in our sky is not alone in the cosmos. It is one of dozens of such natural satellites in our solar system, and countless more in others, each with its own story. They are as varied as the worlds they orbit. Some shine with icy shells, some seethe with volcanic fury, some hide oceans beneath their crusts, and some are mere shards of rock tumbling in irregular paths. They are the silent watchers not just of Earth, but of every planet they accompany, casting light and shadow across the history of the solar system. This documentary journey is an odyssey across time and space, an immersion into the world of moons. We will trace the arc of their narrative, from the ancient myths woven about our moon to the bold exploration of distant moons by spacecraft, from the violent cosmic dances that birthed them to the subtle gravitational embraces that guide their motions. We will stand on the cratered shores of our moon and feel how it shaped Earth's destiny. We will voyage outward to witness fiery Io, icy Europa, and enigmatic Titan. We will delve beneath alien ice looking for the stirrings of life and soar alongside spacecraft as they reveal these new frontiers. Through poetic reflection and scientific insight, we will see moons not as mere rocks circling planets, but as dynamic characters in the grand story of the cosmos. These are worlds that orbit something greater, yet each is a world unto itself. They teach us about creation and chaos, stability and change, and perhaps even about ourselves. Let us begin under the moonlight that has bathed our planet since time immemorial. Let us listen to the silence of the moon and imagine the tales it could tell of Earth's earliest days, of the creatures that evolved under its glow, of the humans who gazed up and found meaning in its face. The story of moons is the story of companionship in the heavens, of smaller worlds bound to larger ones, influencing and illuminating each other in an eternal cosmic dance. And as we explore these stories, we may find that their light guides us not just across the night, but toward understanding our place in the universe. Ancient eyes and mythic tales. Before the age of science, the moon was a canvas for human imagination. In the deep nights of prehistory, Our ancestors looked up with wonder and wove stories to explain the glowing disk that waxed and waned overhead. To them, the moon was more than a rock in the sky. It was a deity, a guide, a timekeeper. Each culture filled the lunar silence with its own voice. Imagine a campfire tens of thousands of years ago, flickering beneath a full moon. A storyteller gestures at the bright orb and recounts how it came to be. Perhaps it is a celestial huntress riding a silver chariot across the sky, as the ancient Greeks believed when they personified the moon as Selene, her face aglow in nightly vigil. Or picture the people of ancient China celebrating the autumn full moon with lanterns and mooncakes, telling of Chang'e, the woman who flew to the moon and lives there forever with her jade rabbit companion. In the myths of the Maya, the moon could be a goddess like Ishel, pouring her light down as a blessing on crops and people. Across the world, countless legends cast the moon as a powerful presence, sometimes male, often female, always influential. These myths carry deeper truths about the moon's importance. Early peoples noticed that the moon's cycle of phases matched the rhythms of nature. The word month itself comes from the moon's cycle, and many ancient calendars were built on its changing face. With roughly 29 days between full moons, the lunar cycle offered a natural unit for measuring time. Under the steady beat of those cycles, humans learned to predict the coming of seasons and tides. The moon became a clock in the sky. In coastal communities, the link between the moon and the ocean's tides was observed and ingrained in law. Fishermen timed their outings by the phase of the moon, knowing the waters responded to its pull. Farmers planted and harvested by planting moons and harvest moons, guided by lunar light and timing. The moon also became a beacon for navigators and travelers. Before artificial lights, its glow on a clear night could illuminate paths and reflect off rivers to guide boats. It's no wonder that full moons inspired gatherings and celebrations. The bright nights were a gift from the sky. In various languages and traditions, each full moon had a name reflecting the seasonal law. The wolf moon of deep winter, the flower moon of spring, the hunter's moon of autumn. Each name was a testament to how intimately human life was tied to lunar rhythms. Yet even as people wove tales about our moon, they began noticing that other lights moved across the heavens too. The 5 wanderers we now call planets were known to ancient stargazers, but it wasn't until the invention of the telescope that humanity discovered those planets had moons of their own. That revelation came in the early 17th century and upended our understanding of the cosmos. On a clear January night in 1610, an Italian mathematician named Galileo Galilei pointed his homemade telescope at Jupiter, a shining point in the sky. What he saw astonished him. Near that planet were 4 star-like dots, invisible to the naked eye, that changed position each night. At first, Galileo thought these might be background stars, but as he tracked them, he realized they were orbiting Jupiter. In a letter, he marveled that he had found 4 wandering stars circling a world other than Earth. These were the moons Io, Europa, Ganymede, and Callisto, the first moons ever observed beyond our own. Their existence was a revelation. Here was proof that not everything revolved around Earth. The discovery of Jupiter's moons showed a mini solar system in its own right, with moons dancing around a giant planet, just as Copernicus had dared to suggest that Earth dances around the sun. Galileo's discovery was met with awe and controversy. The idea that moons orbited Jupiter challenged the prevailing belief that Earth was the fixed center of all celestial motion. Yet the evidence was literally before Galileo's eyes. Night after night, he watched those moons shuttle back and forth around Jupiter. It was as if he had invited the heavens to divulge a secret. Other worlds have their own companions. His findings, published in Sidereus Nuncius, electrified Europe. Suddenly, the moon was not unique. It was one of many, and the universe seemed far larger and more complex. The discovery tide did not stop with Galileo. As telescopes improved, astronomers found that Saturn, too, had moons. First Titan, spotted by Christian Huygens in 1655, and then additional moons by Giovanni Domenico Cassini in the following decades. They noticed Saturn's rings as well, mistaking them at first for moons or odd appendages until their true nature became clear. In 1671, Cassini observed Iapetus, a moon of Saturn that intriguingly seemed bright on one side of its orbit and dark on the other, hinting at exotic surfaces that would much later be explained. By the 18th century, the hunt for moons expanded to the new planets discovered. Uranus, found by William Herschel in 1781, came with at least a pair of moons. Neptune, discovered in 1846, revealed its largest moon, Triton, just days later when astronomer William Lassell pointed his telescope at the new blue world. Each of these findings added a piece to a grand timeline of discovery. From a single moon known to ancient humans, we grew aware that moons are abundant. By the 19th century, the count of known moons was climbing. Jupiter's count rose beyond the 4 Galilean moons as fainter ones were caught on photographic plates in the late 1800s. And that count would explode in the late 20th and early 21st centuries. Today we know Jupiter has nearly 80 moons, Saturn over 80, and even Uranus and Neptune have dozens among them. With modern telescopes and probes, scientists keep discovering tiny new moons, often captured asteroids or shards of past collisions that add to the rich menagerie orbiting each planet. Our cosmic neighborhood was teeming with satellites, some as large as planets, others small and irregular. The word moon itself broadened from meaning the moon of Earth to a whole category of objects orbiting planets. Through it all, the myths and wonder persisted. For common people in earlier times, scientific discovery didn't immediately erase the moon's magic. If anything, seeing Jupiter's moons through a telescope might have felt like peering into the divine realms once reserved for gods. The moons of Jupiter were even given mythological names: Io, Europa, Ganymede, Callisto, after lovers and companions of the god Jupiter, a tradition Johannes Kepler had suggested. It was as if, even in science, we acknowledged that these newfound worlds deserved to be woven back into the tapestry of myth. By the dawn of the 20th century, humanity had mapped the motions of many moons, yet they remained points of light in our instruments, their true nature still a mystery. We knew their orbits, and in some cases their sizes. But what were they really like? Were they like our moon, rocky and cratered? Or were they entirely different, perhaps harboring secrets unknown? The ancient questions persisted in new forms. And as the stars of discovery aligned, we prepared in the mid-20th century to actually visit one of these distant orbs and see for ourselves. But before that bold leap, another question loomed. How did these moons come to be in the first place? Origins in cosmic collisions and embraces. To understand the origin of moons, we must travel back to the chaotic infancy of the solar system, back to a time of swirling disks of gas and dust, of nascent planets coalescing and colliding. Moons are born in violence and in grace, in cataclysms and quiet captures. Their origins are as diverse as the moons themselves, each a story of a smaller world coming to belong to a larger one. One path to becoming a moon is to be born alongside your planet, as siblings in the cosmic nursery. In the young solar system, as giant planets like Jupiter and Saturn formed, they were surrounded by whirling disks of gas and rubble, miniature versions of the disk that formed the sun and planets. Within these circumplanetary disks, material clumped together, layer by layer, eventually growing into the moons we know today. Imagine Jupiter as a newborn king surrounded by a swirling court of dust. Over time, that dust gathered into larger pieces, which drew in more material, building up 4 large moons. Io, Europa, Ganymede, and Callisto, the Galilean moons, likely emerged from Jupiter's disk in this way. like pearls forming in the planet's orbit. In this co-creation, the moons inherited an orderly, flat orbit around their planet's equator, circling in the same direction that Jupiter rotates. They are, in essence, the children of Jupiter's youth, born from the same cradle that fashioned the planet itself. But not all moons share this gentle origin. Some are wanderers that strayed too close to a planet and could not escape its gravity. These moons were not born of their planet, but rather adopted. We call them captured moons. Picture a lone asteroid or perhaps a dwarf planet traveling through space, passing near a much larger world. If conditions are just right, the speed, the angle, maybe the intervention of a third body's gravity, the smaller object can be snared, entering into orbit and becoming a moon. Mars's two tiny moons, Phobos and Deimos, are thought to be captured asteroids, cosmic wayfarers grabbed by Mars long ago. They are irregular in shape, dark and battered, very much like the rubble in the asteroid belt from which they likely came. Their capture may have been assisted by a chance encounter or the drag of the early Martian atmosphere. Phobos and Deimos now dutifully circle Mars, but their origin in the sky is written in their odd shapes and carbon, rich composition, so unlike the red planet they orbit. The giant outer planets, Jupiter, Saturn, Uranus, Neptune, have many moons that fit this description: small, lumpy, and often with wild tilted or retrograde orbits, as if caught by surprise. Neptune's largest moon, Triton, stands out as an extraordinary case of capture. Triton orbits Neptune backwards on a tilted path, a clear sign it did not form alongside Neptune. Long ago, Triton may have been a solitary dwarf planet roaming the Kuiper belt until Neptune's gravity ensnared it. The capture of Triton was likely a tumultuous event. Neptune may have had a system of its own small moons that were shattered or ejected in the process. Triton, now bound to Neptune, slowly settled into a circular orbit, but its backward journey remains a scar of its past. It is a migrant from the solar system's fringes, now forever circling an adopted planet, destined in the far future to spiral inward as Neptune's gravity inexorably saps its energy. Then there is perhaps the most dramatic birth of a moon, creation by cosmic impact. Our own moon is the exemplar of this violent genesis. In the young Earth's history, about 4.5 billion years ago, our planet was not alone in its orbit. A Mars-sized protoplanet, often called Theia, was on a collision course with the early Earth. In a titanic impact, Theia struck Earth with unimaginable force, shattering itself and ejecting a vast cloud of molten rock and debris into Earth's orbit. The Earth was left molten and reeling, its day perhaps shortened to a frantic 5 or 6 hours. But from the wreckage, a new entity emerged. The hot debris flung into space gradually coalesced, drawn together by gravity. Within a span of only a few years, perhaps even just a few months, as some simulations suggest, the glowing ring of debris gathered into a sphere. This newborn moon was an incandescent orb of magma hovering above a roiling Earth. Over time, it cooled and solidified, taking on the face we recognize today. This giant impact hypothesis, as violent as it sounds, elegantly explains many of the moon's known traits. The Earth and Moon, for instance, are made of the same basic stuff. Lunar rocks brought back by Apollo astronauts bear the chemical fingerprints of Earth's mantle. It's as if the moon was once part of Earth, which indeed, in this scenario, it was. The collision gouged out material from Earth and mixed it with pieces of the impactor, creating the moon as a blend. The physics of such an impact also explain why our moon is relatively large compared to Earth, and why it orbits in the same plane as Earth's orbit around the Sun, rather than exactly around Earth's equator. It was born of a collision that had nothing to do with Earth's gentle rotation, and everything to do with orbital dynamics and chance. For years, scientists debated alternative theories. Perhaps the moon was captured, or perhaps Earth spun so fast in its youth that a chunk flung off, or that Earth and moon simply formed side by side. But none of those theories matched the evidence as well as the giant impact. The capture theory struggled to explain the moon's composition, and such a large capture is improbable. The fission idea couldn't account for where the energy to throw off a moon came from. Co-formation didn't explain the differences in iron core size between Earth and Moon. The giant impact, in contrast, gives a dramatic narrative that lines up with the chemical clues. A moon made mostly of earthly material, but lacking heavy iron, and a system still dynamic today. The Earth's moon may be the child of catastrophe, but it forged a new stability. In the aftermath of that impact, Earth gained not only a satellite, but a guardian of sorts, a big moon that would exert a gravitational influence on Earth for eons to come. That story is unique in our solar system. None of the other rocky planets ended up with such a massive moon. It suggests that chance and circumstance, an ill-fated collision at just the right angle and size, can create a moon where otherwise there might have been none. Yet even the giant impact scenario isn't the final word. Scientists continue to refine models of moon formation, debating details. Was Theia completely destroyed? Did the moon form from the debris of both Earth and Theia, or largely from one of them? New theories propose even faster formation or multiple impacts. But the broad strokes remain. Earth's moon was born from fire and chaos, a genesis writ in planetary rubble. Meanwhile, out in the cold reaches of Saturn, another kind of moon formation drama may have played out in miniature. Saturn's iconic rings, made of countless icy particles, might be the cradle for new moons. It's thought that at least one moon of Saturn, a tiny one named Enceladus, may have formed from ring material clumping and merging outside the main rings. And looking at those rings, some scientists speculate they are the remnants of a former moon that wandered too close and was torn apart by Saturn's tidal forces, a fate called Roche limit disruption. If so, Saturn's rings are both a graveyard and a nursery, the destruction of one moon giving birth to perhaps others, as the debris in the rings slowly accretes. Across the solar system, the story repeats with endless variations. Some moons grew calmly from disks, some were snared from elsewhere, some were born in fire and fury. Co-creation, capture, collision. These are the three classic ways to make a moon. Each moon's current orbit and composition carry clues of its birth. A prograde, aligned orbit hints at a native child of the planet. A tilted or backward orbit points to a captured outsider. A large moon, rich in the planet's own materials, whispers of an ancient impact. Understanding these origins is not just cosmic genealogy, it also sets the stage for everything that comes after. A moon's beginning determines its size, its composition, its proximity to its planet, all factors that influence whether it might have an atmosphere, geological activity, or even the ingredients for life. Our journey through the origins of moons, then, is more than an origin story. It's the prologue to every tale of tides, eclipses, volcanic eruptions, and possible life that moons might eventually host. From the dust of creation to the flames of collision, the birth of moons is a drama that has shaped the very architecture of our solar system. And nowhere is the effect of a moon's existence more profound than right here on Earth, where our moon's presence set the stage for the story of life. The moon's imprint on Earth. Our moon, born of Earth's fury, has in turn been a gentle sculptor of Earth's destiny. Once the moon coalesced and cooled, it settled into orbit around our planet, and a gravitational relationship began that continues to this day. This constant companion, comparatively large and close, exerted forces on the young Earth that would slowly weave the conditions for a stable, life-bearing world. The influence of our moon is profound, shaping the tides, steadying the seasons, perhaps even nudging life's evolution from sea to land. Stand on a beach and watch the ocean, and you are seeing the moon's handiwork. The tides, those regular risings and fallings of the sea, are primarily a consequence of the moon's gravitational pull. As the moon orbits Earth, its gravity draws a bulge of water toward it, causing high tide on the side of Earth facing the moon. and simultaneously on the opposite side due to inertia. Our rotating Earth carries coastlines into these bulges and out again, producing 2 high tides and 2 low tides each day. Since antiquity, coastal peoples have timed their lives by this tidal rhythm. Fishermen knew the best harvest of clams or fish often came with the outgoing tide, and navigators planned departures by the high tide's depth. But beyond human use, tides were a mixing spoon in Earth's primordial soup. In the planet's youth, when the moon orbited much closer, tides were enormous. Imagine ancient shorelines with waves tens of meters higher, flooding far inland, and then retreating twice a day, every day. These vigorous tides may have created countless tide pools along rocky coasts, trapping water and concentrated chemicals, then stranding them to dry in the sun before flooding again. Some scientists speculate that these wet, dry cycles, driven by lunar tides, could have been crucial in assembling the complex molecules of life. Perhaps the moon played midwife to life's emergence, providing the gentle pulsation that encouraged simple chemicals to organize into self-replicating patterns. Over billions of years, the moon has been slowly moving away from Earth, and the days on Earth have been growing longer. In Earth's infancy, a day might have been only 6 or 8 hours long, blurred by the rapid spin left over from the moon, forming collision. But the moon's gravity raised tidal bulges, not just in the oceans, but in Earth's solid body as well. As Earth rotated, these bulges lagged slightly behind the line toward the moon, effectively pulling back on Earth's rotation like a brake. The energy of Earth's spin transferred to the moon's orbit, pushing the moon farther away. Through this cosmic friction, our day lengthened from a frenetic spin to the 24-hour cycle we now find so normal. We live, in a sense, on a tempered planet, tempered by the gravitational tug of the moon. If you could speed up time, you would see Earth's rotation slowing and the moon spiraling outward in a graceful, ever-widening helix. And as trivial as a few extra hours in a day might sound, the slowing of Earth's spin and the stabilization provided by the moon had cascading effects on climate and life. One of the most crucial roles the moon plays is as a stabilizer of Earth's axial tilt. The tilt of Earth's axis is what gives us seasons. Leaning toward the sun brings summer, leaning away brings winter. But that tilt is not fixed in space. Gravitational tugs from the sun and other planets cause Earth to wobble like a spinning top. Without our moon, these wobbles could have been chaotic and extreme. Mars, for example, lacks a large moon, and its tilt has swung wildly over eons, perhaps ranging from near zero to as much as 60 degrees, contributing to violent climate shifts. Earth, by contrast, has the moon's steadying gravitational hand. The moon's mass helps keep Earth's tilt oscillating only mildly over very long timescales, preventing wild swings. This means our seasonal cycle has remained relatively stable for millions of years at a time, providing a consistent backdrop for life to adapt to. If Earth's tilt were to vary dramatically, ice ages might deepen and last longer, or tropics might swing from boiling to freezing, conditions that would challenge the persistence of complex life. The moon's presence has been like the weight on a gyroscope, damping the wobbles and ensuring that the pendulum of climate doesn't swing too violently. Climate stability is more than a comfort. It may have been a key ingredient for life's long, slow evolution. Under a stable seasonal rhythm, ecosystems have time to establish, and species can adapt at an evolutionary pace, not constantly reset by catastrophic climate lurches. Consider that our current mild wobble leads to cycles like the ice ages. Even those relatively mild oscillations challenged early humans, but life as a whole persisted and diversified through them. Had Earth's obliquity swung from 0 to 60 degrees on a whim, the planet might have seen periods where the poles pointed directly at the sun and then later rolled on its side. The moon's steadying gravitational anchor likely spared Earth such extremes. Beyond physics and climate, the moon has subtly guided the rhythms of living creatures. The night's brightness under the moon has steered behaviors for untold species. Sea turtles, for instance, hatch on beaches by the thousands, and instinctively crawl toward the brighter sea horizon, using the moonlit ocean to find their way. Salmon and grunion fish coordinate their spawning with the highest tides around the full and new moons, laying eggs in sand that will be washed out on the next spring tide. Corals in the Great Barrier Reef spawn en masse on certain nights, linked to the moon's phase, releasing millions of eggs and sperm in miraculous synchronicity under a full moon's light. Even some birds use the moon and stars to navigate during migrations. And ancient human cultures, without electric light, lived by the lunar calendar, planning hunts and festivals by the fullness of the moon. Our very sleep cycles and moods have, anecdotally, been tied to the moon's presence. It's possible that life as we know it has a debt to the moon that we are only beginning to understand. In Earth's deep past, perhaps around 400 million years ago, the moon was closer and tides were stronger. Some research suggests that these strong tides could have influenced the great leap of life from water to land. Fish in tidal pools, trapped by receding water, may have needed to flop to adjacent pools or adapt to breathing air for hours until the water returned. Those that managed such feats survived to pass on traits for air, breathing, and limb, like fins. Over generations, these pressures might have encouraged the evolution of amphibious fish, a stepping stone to true land vertebrates. In this way, the moon's tidal pull might have been an unseen hand, coaxing creatures onto dry land and into a new world of evolution. The moon's influence extends to the invisible choreography of Earth's motion as well. The gravitational dance between Earth and Moon has locked the moon's rotation to match its orbit. But Earth, too, is moving in response to the moon. The two actually orbit a common center of mass, a point inside Earth, but offset from its exact center. This wobble means Earth's path around the sun is slightly perturbed by the moon's presence. And during solar eclipses, when moon and sun align, the moon's shadow races across Earth, a tangible reminder of how perfectly the moon can sometimes position itself thanks to its influence on our orientation. All these effects, tides, day length, axial stability, biological rhythms, underscore a profound truth. Without the moon, Earth would be a very different world. Perhaps life would have found a way regardless. Many scientists debate just how critical the moon's presence was for life's eventual emergence and persistence. Some argue that life could adapt to any sky, while others point out that our large moon might have accelerated evolution or even been necessary to get it started. What is certain is that the moon has been intertwined with life's saga at every turn. From the gentle night light that enabled nocturnal creatures to thrive, to the tidal heartbeat that mixed nutrients in the seas, to the steady seasons that allowed complex ecosystems to develop, the moon has been a constant, subtle, guiding force. Tonight, when you see the moon's bright disk or its thin crescent hanging in the sky, remember that its presence is not just aesthetic. That gleaming orb has been working for eons, pulling on our oceans, slowing our spinning globe, and lighting a path for life to follow. It is easy to imagine an ancient Earth without a moon, a dark night sky, weaker tides, a planet wobbling in uncertainty. Perhaps such an Earth would still harbor life. But would it have been the same rich tapestry we know? Our moon has been a blessing of stability amidst cosmic chaos, an ever-present partner that turned what could have been a more erratic planet into a gently pulsating cradle for life. In the grand tale of Earth, the moon is a character impossible to ignore, an influence from the skies that has quietly guided the unfolding of our own story. Now, having appreciated how our singular moon has shaped us, we turn our eyes outward again. For as unique as Earth's moon is, it is but one of a vast menagerie. Out beyond our planet, orbiting the other giants of the solar system, are moons of ice and rock that reveal an astonishing diversity of nature's creations. Our moon's story is intimately tied to Earth, What wonders and surprises might the moons of other worlds hold? It is time to leave home and voyage into the outer solar system, where moons abound and each holds its own secrets. A tour of the solar system's moons, diversity of worlds. Leaving Earth behind, we venture across the solar system to visit the remarkable moons that orbit other planets. Each is a world with its own character, as different from one another as deserts are from glaciers, as fire is from ice. In this journey, imagine flying alongside a spacecraft, sweeping first into the realm of the inner solar system, and then outward past the giants, touching down in thought on one moon after another. Our first destination lies near the roiling clouds of Jupiter. As we approach the giant planet, a speck glowing in golden hues comes into view. Io, the innermost of Jupiter's Galilean moons. At first glance, Io's surface is mottled yellow and orange, like a pizza covered in sulfurous cheeses and sauce. This bizarre coloring hints at the extreme volcanism underneath. Io is the most volcanically active body in the solar system. As our mental spacecraft hovers above Io's alien plains, we see volcanoes erupting in great plumes, spraying molten sulfur hundreds of kilometers high. Lakes of lava glow in red patches across the night side. The ground is coated in sulfur compounds, painting Io in brilliant shades of yellow, white, and green. How did this small moon become a hellfire of activity? The answer lies in the relentless pull of gravity and dance of orbits. Io is caught in a gravitational tug of war between Jupiter and the outer Galilean moons. As it orbits, Io is continuously flexed by Jupiter's immense gravity. Imagine the solid ground rising and falling by tens of meters, squeezed like a stress ball. This tidal heating cooks Io's interior and fuels its prodigious volcanoes. Here on Io, we witness a world in constant upheaval, its surface renewed by fire every few years. It is a land of perpetual change, with mountains taller than Everest, that may only last a few million years before collapsing under Io's geological frenzy. In mythology, Io was a maiden pursued by Zeus, transformed into a cow. In reality, Io is a tortured world, eternally writhing under the grip of its giant overlord. Next, we glide outward to Io's neighbor, Europa. Instantly, the scene changes from fire to ice. Europa is slightly smaller than our moon, and it gleams like a pearl, its surface a smooth, bright expanse of water ice. As sunlight glints off its frozen crust, we see a network of dark streaks crisscrossing the moon, like the cracked shell of an egg. These are Europa's famous lineae, fissures in the ice that have been filled and stained by materials from below. Unlike Crater, scarred Callisto, or Mercury, Europa's surface has relatively few craters, indicating it is young and active. But unlike Io, we do not see volcanoes of molten rock. If Europa is active, it is a hidden activity beneath the ice. Scientists have long hypothesized, and now have strong evidence, that beneath Europa's icy shell lies a global ocean of liquid water, kept warm by the same tidal forces that torment Io. This means that as we float above Europa, below us could be an ocean tens of kilometers deep with more liquid water than all of Earth's oceans combined, sealed under a crust of ice perhaps 20 kilometers thick. Occasionally, our spacecraft might catch sight of a geyser, a faint misty plume erupting at the limb of Europa, evidence that water from below sometimes escapes to space through cracks, just as a whale might exhale a breath into the sky. On Europa's surface, we see shattered plates of ice that look as if they've rafted and drifted, and reddish-brown stains where salts or organics may have upwelled. It's a relatively flat world, no towering mountains, but rather a jigsaw puzzle of ice. If we could land and drill down, we'd eventually break through into an alien sea. In our mind's eye, we plunge into the dark waters of Europa, shining a light into the depths. What might we find? Perhaps the seafloor of Europa has hydrothermal vents, like those on Earth's ocean bottom, where mineral-laden hot water gushes out of rock, providing energy and nutrients. On Earth, such vents teem with life: tube worms, clams, strange microbes, entire ecosystems cut off from sunlight. Could Europa's oceans similarly harbor life, nourished by chemical energy and warmth from below? It's a question so enticing that humans are planning missions to one day pierce Europa's secrets. For now, as we leave Europa, we feel the profound hush of this moon, a still, glistening surface above a hidden, restless sea. If Io is the solar system's volcano, laden heart, Europa is its enigmatic, icy soul, holding its secrets deep under frozen plains. Continuing outward, we meet Ganymede, the giant among moons. Ganymede is the largest moon in the solar system, bigger even than the planet Mercury. As we approach, Ganymede looks somewhat like a scaled-up version of our moon or Mercury, with light and dark patches. But Ganymede has a surprise. It possesses a magnetic field of its own, something no other moon has. Our spacecraft instruments detect the auroras shimmering in Ganymede's thin atmosphere, proof of its magnetic bubble within Jupiter's powerful magnetosphere. Ganymede's surface is a mix of very old, dark, cratered regions and somewhat younger, lighter regions laced with grooves and ridges. It's as if Ganymede tried to undergo tectonic activity in its past, the crust stretching and breaking into patterns, then largely froze in place. Like Europa, Ganymede is believed to have an ocean beneath its surface, but likely sandwiched between layers of ice, perhaps a deep, buried sea that is less accessible. Still, the presence of water, a differentiated interior with a metal core, and that enormous size make Ganymede a world of interest. If we could stand on Ganymede, we'd see Jupiter looming huge in the sky, and perhaps thin wisps of oxygen around us. We might walk on water, ice that is, that conceals a distant ocean below our feet. Next comes Callisto, the outermost large moon of Jupiter, a stark contrast to the others. Callisto, shrouded in darkness at the fringes of Jupiter's domain, appears as an ancient cratered relic. Its entire face is pockmarked like a cosmic shotgun target, saturated with impact scars from eons past. It has no discernible mountains or volcanoes or ridges, just endless craters upon craters, with faint rings around the largest impacts, like ripples frozen in ice. If the inner moons of Jupiter are active or were active, Callisto seems to have never been. It is, in a way, a long dead world, a remnant of the early solar system preserved in cold storage. Yet even quiet Callisto might hide a small secret. Data from spacecraft hint it too could have a slumbering ocean deep inside, beneath hundreds of kilometers of ice and rock. If that ocean exists, it has likely been static for billions of years, undisturbed by significant heating or tidal flexing. Callisto stands as a testament that not every moon becomes a geologic wonderland. Some simply exist, surviving from antiquity with the stories of the solar system's violent birth written in their craters. Leaving Jupiter, we sail on to Saturn, where a multitude of moons awaits in a realm of icy enchantment. The first to greet us is Titan, Saturn's largest moon and one of the most compelling places in the solar system. As we approach Titan, we do not see a cratered moon at all. Instead, we see a hazy orange sphere, its surface completely hidden by a thick atmosphere. Titan is the only moon with a dense atmosphere. In fact, at Titan's surface, the atmospheric pressure is about 1.5 times that of Earth's. Standing on Titan would feel a gentle weight of air around you. This atmosphere is rich in nitrogen, like Earth's, but suffused with methane. High in Titan's skies, methane and other hydrocarbons form thick smog that filters the sunlight to a dim, amber glow. If we descend through Titan's clouds, we would witness a landscape both alien and uncannily familiar. There are rivers and lakes here, but filled with liquid methane and ethane instead of water, for Titan's surface temperature is a frigid 179 degrees, far too cold for liquid water. In Titan's dim noon light, we might see ethane rain falling from the clouds onto broad, mirror, like lakes that stretch to the horizon. There are rolling dunes made of hydrocarbon sand, likely formed from organic molecules that have settled out of the sky. There are even seasons on Titan. Over its 30-year orbit around the Sun, its polar lakes shrink and grow, and clouds cluster in different regions. Titan is a world that eerily parallels Earth in some ways. Wind, rain, rivers, lakes, maybe even cryovolcanoes that erupt not molten rock, but water mixed with ammonia from its icy interior. Beneath Titan's frozen crust, scientists suspect another hidden ocean of liquid water and ammonia might reside, kept warm by the moon's internal heat. Titan thus could have two kinds of habitable zones, one in its dark subsurface ocean and another in the liquid hydrocarbons on its surface, albeit any life that might exist in the latter would have to be very different from life as we know it. As we roam Titan's surface in our imagination, methane rain falls on our helmet visor and pools at our feet. We see the glint of Saturn's rings in the sky through a gap in the clouds. Titan feels like a primordial Earth, but one locked in deep freeze where chemistry, not biology, paints the scene. Not far from Titan, another small moon beckons with a dazzling display. Enceladus. Compared to Titan's enormous diameter of 5,150 kilometers, Enceladus is tiny, only about 500 kilometers across. Yet what Enceladus lacks in size, it makes up for in wonder. This bright, ice-covered moon orbits within Saturn's E-ring, and as we draw near, we see why that ring exists. Enceladus is actively spraying its material into space. Along Enceladus's south pole, great fissures in the ice, fondly called tiger stripes, crack the surface. From these cracks, geysers of water vapor and ice crystals continuously erupt, like a curtain of fine, misty jets. Our spacecraft flies through one of these plumes, and instruments taste the vapor. They find water, simple organic molecules, and even microscopic grains of silica, hinting at hydrothermal vents down in a warm ocean beneath the ice. Enceladus, like Europa, hides an ocean under its shell, and through those tiger stripes it vents the ocean to space, giving us free samples of what lies beneath. The sight is breathtaking. Against the blackness of space, dozens of geysers catch the sunlight, forming a shimmering halo over the moon's south pole. The surface around the area is young and smooth, repaved by fresh icefall from these plumes. It was the Cassini spacecraft that discovered this surprise in 2005, changing forever how we see this moon. We now picture Enceladus as a small, cold world that nonetheless has become a cosmic snow globe of activity. Its internal heat likely comes from tidal flexing, which keeps its core warm enough to maintain a liquid ocean. The water from that ocean, maybe 30 kilometers below, forces its way up through cracks and sprays out, instantly freezing and falling back, or floating away to feed Saturn's rings. If we land near a tiger stripe, we'd be on terrain of pure water ice, possibly feeling the ground tremble from subsurface activity. It would be unimaginably cold on the surface, but just below might lie liquid water and perhaps geothermal vents rich in minerals, again raising that tantalizing possibility. Could life exist there, swimming in a hidden sea and periodically being shot out through a space geyser? Now we venture further out, past Uranus with its retinue of frozen, dark moons. We arrive at Neptune, the outermost giant, where a captured moon reigns. Triton. Triton is Neptune's largest moon and unlike any other in the outer solar system. When Voyager 2 flew by in 1989, it revealed Triton as a pinkish, icy sphere with a polar cap of nitrogen ice and a strange cantaloupe-textured terrain. Triton was a revelation. Despite being far from the sun and in the deep freeze, it was not entirely inert. Voyager's cameras caught sight of dark, wind-blown streaks and, incredibly, active geysers near Triton's south pole. But these were not water geysers like Enceladus's. Triton was spewing nitrogen gas. Invisible sunlight, though weak, was enough to heat darker patches on Triton's surface, causing pockets of nitrogen ice to turn to gas and erupt through the surface, carrying dark soot like particles that then fell back. streaking the landscape. We witness one of these geysers ourselves, a faint geyser, backlit by the dim sun, reaching some kilometers high before the material drifts downwind in Triton's thin atmosphere. Triton's surface is young in many areas, with few craters, indicating it has been resurfaced, perhaps by icy volcanism or other processes. We glide over plains that may have been smoothed by slush or eruptions of water, ammonia mixtures long ago. There are odd, lumpy landscapes that look like melting ice cream, possible signs of past cryovolcanoes. Triton, being a captured object, has an eccentric past. Its capture by Neptune would have generated immense tidal heating at first, potentially melting its interior. Over time, Triton settled into a retrograde, circular orbit and cooled, but the geological memory of that event is written in its relatively complex geology. Triton orbits Neptune opposite to the direction Neptune rotates, which is unique for a moon of that size, another clue of its exotic origin. It is also slowly spiraling inward. One distant day, far beyond our lifetimes, Triton may come close enough to be torn apart by Neptune, perhaps forming new rings. But for now, it's a frozen moon with a thin air of nitrogen, a wintry outpost showing that even in the far reaches of the solar system, moons can be dynamic. As our journey through the solar system's moons comes to an end, we take a moment to appreciate the staggering variety we've encountered. We flew from Io's lava fountains to Europa's secret ocean, from Ganymede's giant bulk to Titan's orange skies and methane lakes, from Enceladus's crystal plumes to Triton's geysers and icy plains. We saw moons that could fit in a small sea on Earth, and moons bigger than planets. We saw fire, ice, atmospheres, magnetic fields, and underground seas, all in worlds that orbit other worlds. Each of these moons is a chapter in the solar system's story, a unique expression of how diverse planetary bodies can be. It's humbling to remember that for most of history, these places were just points of light, or in Titan's case, not even visible under its shroud. Only recently have we glimpsed their surfaces and felt their environments through our robotic emissaries. They have transformed our understanding of what a moon can be. No longer can we think of moons as mere dead rocks orbiting planets. Many are complex, geologically alive, and in several cases, potentially harboring the conditions for life. Our tour has shown us boiling sulfur and freezing methane, stark craters, and ethereal atmospheres. And yet, among all these differences, each moon shares a common role, circling a parent planet, locked in a gravitational embrace. They light up their planet's night skies, just as our moon lights ours, each one a smaller part of a greater whole. With this rich tapestry of moons in mind, we are drawn to wonder, where else in those distant, cold, or hot moons might life have found a foothold, as it did on Earth's congenial world under the influence of our moon? The next leg of our journey delves deeper into that question, focusing on those moons that tantalize us with conditions that could be ripe for life. Oceans and the search for life on moons. Among the myriad moons we've visited in our imagination, some stand out as more than just geological wonders. They stir the question of life. Could any of these alien moons harbor living organisms, or at least the ingredients for life's chemistry? The possibility is no longer science fiction. It is a serious focus of modern planetary science. Particularly, the moons that conceal liquid water beneath their surfaces have captured our hopes. On Earth, where there is water, there is life, virtually everywhere. So what of those moon oceans in eternal night? Could life be swimming in Europa's abyss, or lurking in Enceladus's geysers, or even riding the methane raindrops on Titan? The case for Europa as a habitat begins with its deep saltwater ocean, which could be tens of kilometers thick and global, containing perhaps twice the volume of all Earth's oceans. Liquid water alone is enticing, But life also needs energy and chemistry. Europa seems to offer those as well. Jupiter's constant tidal kneading not only keeps Europa's ocean liquid, it likely drives geological activity at the sea floor. If Europa's rocky mantle interacts with its ocean, perhaps through hydrothermal vents, there could be warmth and nutrients feeding into the water. On Earth, life thrives around hydrothermal vents in the lightless depths, drawing energy from chemical reactions. Europa could host analogous ecosystems, microbes or more complex life feeding on the chemical energy from inside Europa. The European Ocean is sealed off by ice, but that ice might also do something important. It could cycle nutrients. We saw Europa's surface is crisscrossed by cracks and regions where ice seems to have moved around. Some scientists think that surface oxidants could be transported downward through the cracks or subducting ice plates, providing chemical food for life below. In essence, Europa might have the three key ingredients: liquid water, chemical building blocks, and an energy source. No one knows if anything actually lives there. It remains a profound mystery. But if one day we were to drill through Europa's ice and drop a submersible, we might find a whole ecosystem of alien microbes or pale blind fish analogues gliding through the dark. Or we might find nothing at all but a sterile sea. Yet as long as that ocean is there, Europa will beckon as one of the best places beyond Earth to search for life. Then there's Enceladus, the little moon that surprised us with a direct invitation to sample its ocean. Enceladus's plumes jetting into space provide a literal taste of its subsurface sea. When the Cassini spacecraft flew through those geysers, its instruments detected organic molecules, including some fairly complex ones, and tiny grains of rocky particles that could only be formed by hot water interacting with rock. This was a smoking gun for hydrothermal vents on Enceladus's seafloor. Moreover, in 2023, scientists announced that those icy grains contained phosphorus, an element crucial for life, which had been a missing puzzle piece in evaluating Enceladus's habitability. In one swoop, Enceladus offers water, organics, and key minerals, an entire chemistry set for life. The energy clearly exists too. Something drives those plumes, and presumably it's heat from below. Enceladus is small, which suggests its ocean might be in contact with a rocky core that's being flexed and heated. If one could dive into Enceladus's ocean, would it be a dead, dark sea? Or might one find microbial mats around warm vents? Or maybe some exotic life forms that evolved entirely independently of Earth? We cannot help but wonder. Unlike Europa, where a thick crust makes direct exploration challenging, Enceladus conveniently sprays its ocean into space, making it easier for a spacecraft to analyze for signs of biology, perhaps complex organic compounds, or even traces of cells or their remnants in the ejected ice. Titan presents a very different potential for life. On Titan's frigid surface, the lakes and rivers of methane and ethane form a chemistry that is likely too cold and too alien for Earth, like life. Water there is locked up as rock, hard ice. If life exists on Titan's surface, it would have to be something that drinks liquid methane instead of water, a truly novel biochemistry that we can only speculate about. Some astrobiologists have mused about methanogenic life, creatures that use liquid hydrocarbons as a solvent and perhaps breathe hydrogen and exhale methane, but this is highly hypothetical. Titan's surface environment is so cold that reactions happen slowly. It might be tough for life to get started. However, Titan is rich in organic molecules. The atmosphere and surface are a laboratory of prebiotic chemistry, where sunlight break apart methane and nitrogen, forming carbon, rich compounds that rain down. Titan's smog is literally a shower of organic matter. Some liken Titan to a deep freeze version of the early Earth's chemical soup, minus the liquid water. While surface life is speculative in the extreme, Titan also, intriguingly, likely has a subsurface water ocean beneath its ice crust. So Titan might have two environments of interest: a cold surface with exotic chemistry, and a hidden water ocean where more familiar life could conceivably exist. If there is life in Titan's ocean, it would be completely cut off from the surface, evolving in the dark with perhaps only the faint trickle of chemical nutrients from rock and ammonia antifreeze to keep it liquid. It's a far cry from the rich brew of Enceladus or Europa, but Titan surprises us at every turn, so who can say? Even Ganymede and Callisto, those Jovian moons we thought rather inert, may harbour deep oceans beneath thick ice layers. Ganymede's ocean is likely sandwiched between ice, which might limit its habitability. Callisto's ocean, if it exists, is also entombed. These places seem less likely abodes for life, but until we explore them, the possibility, however remote, remains. Triton at Neptune, too, could have had a subsurface ocean when it was younger, and maybe pockets remain today, though it's hard to imagine life surviving the drastic upheavals of Triton's capture and cooling. What about moons without oceans? Could life exist in some other form? Perhaps not life as we know it. Moons like Io are too hostile, bathed in radiation and molten rock. Luna is bone, dry and airless at the surface, though we've found traces of water ice in its shadows. It seems lifeless. Most small moons are like asteroids, inert, with no air or water. So it is the water, rich moons that raise our hopes. Our exploration so far has been like detectives gathering clues. Water plumes here, organic molecules there, heat signatures hinting at liquid below. No definitive evidence of life has been found beyond Earth, but these moons offer some of the most promising hunting grounds. In a way, the search for life on moons has reshaped our idea of the habitable zone. We once thought you had to be at just the right distance from the sun for a planet to have liquid water and life. But Europa and Enceladus show that a moon can have liquid water far outside the traditional habitable zone thanks to tidal heating. So perhaps in other solar systems, moons of giant planets might outnumber planets as places to find life. The thought is exhilarating. Life, bearing moons orbiting massive Jupiter, like planets in distant star systems, or under the ice of Saturn's modest satellites. If we find even simple organisms in one of these moons' oceans, it would suggest that life might spring up wherever conditions allow, even in the dark, under kilometers of ice given water and energy. If, on the other hand, we search thoroughly and find nothing living in these seemingly habitable oceans, that would also teach us something profound, that perhaps life is more rare or needs more specific circumstances than we think. For now, these questions propel us to keep exploring. Planned missions like Europa Clipper will sniff out Europa's environment for chemical signs of life's work. Future concepts imagine sending a probe through Enceladus's plume specifically equipped to detect biomolecules or even cells. There is even a dream of one day sending a lander to drill into Europa's ice, or a submarine to swim in its ocean. As we contemplate these moons with potential for life, we feel a subtle shift in perspective. No longer are we the center of the living universe. Life could be scattered on these little ocean worlds in our own celestial backyard. Imagine looking up at Jupiter in the sky and knowing that on one of those pinprick moons orbiting it, something stirs in an alien sea. Such a realization would forever change our relationship to the cosmos. In the grand scale of the solar system, these moons are tiny, but in their tiny niches they may hold some of the biggest answers. Are we alone, or is life a common melody threaded through many worlds? To find out, we must continue to explore these moon worlds with open minds and meticulous science. And as we do, we deepen our appreciation of how special and varied moons can be. Not just passive satellites, but active worlds that could nurture life in the most unexpected of places. Having pondered life and hidden oceans, we turn now to look at moons in another light, as dynamic worlds with geological stories of their own. Alive or not, these moons are far from static. Some are alive geologically, with volcanoes of fire or ice, shifting crusts, and evolving surfaces. Let us now examine how moons, much like planets, can be volcanic, tectonic, and surprising in their ongoing activity. Geological marvels, volcanoes, geysers, and tectonics on moons. In exploring moons, we have discovered that many are not inert balls of rock, but geologically dynamic worlds. Just like planets, moons can have volcanoes that erupt molten rock or icy slush, quakes that shake their crusts, and tectonic forces that reshape their surfaces. These processes remind us that size and status don't limit geological vitality. What matters is energy. If a moon has internal heat, from tidal flexing, radioactive decay, or leftover heat of formation, it can become a stage for remarkable geological activity. Let's examine some of the ways moons act as living worlds of stone and ice. First, consider volcanism. We traditionally think of volcanoes as mountain cones on Earth, spewing lava, or the great basalt floods that created our moon's dark seas billions of years ago. But on Io, as we saw, volcanism is an ongoing symphony of fire. Io's volcanoes, like the towering plume of Loki Patera or the curtains of lava at Prometheus, are driven by tidal heating. This is a fundamentally different heat engine from Earth's radioactive core-driven volcanism, and it makes Io's entire surface a volcanic canvas. Lava flows hundreds of kilometers long repaint Io's face, and enormous calderas dot its surface. Io's volcanism is so intense that it constantly replenishes a thin atmosphere of sulfur dioxide, and even feeds a giant torus of plasma around Jupiter. We have effectively seen a tiny moon outdoing even Earth in volcanic output, all because it is squeezed by gravity like putty. Our own moon once had its fire, a fact written in the vast mare which are solidified lava from ancient eruptions. Though the moon is quiet now, for the first billion years of its life it saw eruptions flood craters and lowlands with basalt. Even small moons can erupt. Take Jupiter's moon Io as the prime example, but also Saturn's tiny moon Enceladus, where cryovolcanism, volcanoes of water, not fire, operates. Cryovolcanism is essentially the cold region equivalent of volcanism. Instead of molten rock, what erupts is liquid water, or water mixed with ammonia or methane that can flow at very low temperatures. Enceladus's geysers are cryovolcanic in nature. There might also be cryovolcanoes on Triton, and possibly on Titan. In fact, Titan's surface shows some features that scientists interpret as potential ice volcanoes. For example, a feature named Doom Mons appears to be a broad rise with a pit, reminiscent of a volcanic caldera, and nearby flows of what could be once melted ice. If Titan has cryovolcanoes, they could be venting water and ammonia from its interior, perhaps occasionally refreshing the surface or atmosphere with new material. Tectonics, the forces that crack and shift a crust, are also present on moons. We have only confirmed active plate tectonics on Earth, but evidence of tectonic-like processes can be found on moons. Europa's cracked ice plains strongly hint at an ice crust that has pulled apart and maybe even subducted in places, as one plate of ice slides under another, similar to Earth's geological plates. Ganymede's network of grooves and ridges suggests that at some point in its past, its icy lithosphere was stretched and pulled, creating faults and troughs, akin to rift zones on a planet. Even small Enceladus shows tectonic fractures. Its surface has regions of tight, rippling faults and folds, especially around the South Pole, indicating the crust has been stressed, distorted by cycles of freezing and thawing, or the stresses from its orbit. Miranda, a small moon of Uranus only about 470 kilometers across, is a bizarre example. It sports giant canyons and patchwork terrain that might have formed from tectonic upwellings or even a reassembly after a shattering impact. It's as if Miranda was broken apart and gravity put it back together in a jumbled way, leaving huge cliffs and chevron, like surface regions. Resurfacing is another sign of geological life. A surface that doesn't stay cratered but is renewed. We gauge a surface's age by how cratered it is. The more craters, the older. When we see a moon like Callisto, saturated with craters, we suspect it's been geologically quiet for billions of years. In contrast, Europa's relatively smooth, crater-poor surface means something erased the craters, likely the movement of ice or flooding of fresh material. Io's lack of many impact craters is explained by its volcanoes constantly burying them. Enceladus has certain regions with almost no craters. Clearly, it has been resurfaced by ongoing geyser activity, laying down fresh snow, like ice. Titan's craters are few and far between, likely because active processes like wind erosion, liquid methane rain carving river channels, and perhaps cryovolcanism all conspire to modify the surface. A fascinating example of resurfacing is Iapetus, Saturn's odd two-toned moon. While not exactly resurfaced by internal activity, it has sweeping dark material coating one hemisphere, likely fallout from dust or perhaps cryovolcanic material from outside. The contrast on Iapetus shows how surfaces can change due to even external processes. Then there are moonquakes and other internal rumblings. Apollo astronauts left seismometers on the moon, and they detected that the moon isn't dead silent. There are moonquakes, some from tidal stresses, some from thermal changes, and some from the occasional meteorite impact. The moon's quakes are mild compared to Earth's, but they tell us our moon still settles and adjusts. In recent years, we've even found evidence that the moon shrinks very slowly over time as it cools, forming fresh scarps and cliffs where the crust has cracked and pushed up. Some of these faults look so sharp and young that they may have caused quakes in the moon's recent past. If our large moon can still creak and quake, imagine the much more active churning inside moons like Europa or Enceladus. Some moons have magnetic personalities. Ganymede's intrinsic magnetic field points to a liquid metallic core churning inside, which is a form of internal activity. Even if that doesn't manifest in surface geology, it's an internal dynamic process, and we have induced magnetism detected at Europa and Callisto, hinting at conductive oceans moving within. We also see evidence of expansion or contraction on some moons. For instance, Mercury has shrinkage cliffs. Similarly, as mentioned, our moon has them from contraction. Enceladus's ridges and troughs might indicate cycles of freezing and melting. Triton's weird cantaloupe terrain could be from slow, convective overturn in the ice, a sort of relaxation of the surface. Let's not forget the icy ring moons and how they interact. Some tiny moons like Pan and Atlas around Saturn are sculptors of the rings, their gravity opening gaps and shaping edges. This is a gravitational interaction, but results in geological, like patterns in the ring debris. And some moons like Saturn's Janus and Epimetheus even gently collide and exchange orbits occasionally, though they themselves are too small for internal geology. Their dance is a dynamic process on a celestial scale. What we learn from all these observations is that moons can be as geologically diverse as planets. Being a moon only means it orbits a planet. It says nothing about whether it has volcanoes or not. The presence of internal heat is key. Tidal heating has emerged as a major driver. It powers Io's infernos and Enceladus's fountains, and likely Europa's underwater volcanism. Radioactive decay and leftover heat can drive early activity. Sometimes a huge impact can melt a moon's insides briefly. As we visit these moons as geological worlds, one cannot help but anthropomorphize a little. Io is the restless firebrand, Europa, the secretive ocean, Holder cracking its knuckles now and then, Enceladus, the tiny overachiever, spraying its cosmic fountain, Titan, the atmospheric enigma, slowly raining and eroding, and Triton, the captured rebel, still venting occasional sighs of nitrogen. Even sedate old Callisto, or far out Oberon, and Titania around Uranus each have stories, perhaps long dormant, but written in chasms and craters, waiting for a future mission to decipher. The more we see, the more we appreciate how active and varied moons can be. Gone is the notion that moons are boring backwaters. Instead, we find on these smaller orbs an incredible laboratory of geology. From the hellish volcanism of Io, hotter in spots than Earth's volcanoes, to the gentle ice volcano cryovolcanism of the outer moons, to evidence of tectonics that on Earth would signal plate movements. Moons have witnessed and enacted many of the same processes that shape planets, and some unique ones too. By studying these processes on moons, we also learn more about Earth. Io's tidal heating is an extreme case that illuminates how gravitational energy can geologically transform a body. Europa and Enceladus show what happens when internal oceans interact with crusts, something that might have analogies in Earth's past. Even the moon's slow cooling and shrinking gives insight into how terrestrial planets lose heat. With our geological tour of moons concluded, we have seen worlds alive in one way or another. Now, we turn our attention to some of the anomalies and oddities that defy the typical patterns. The misfits of the moon world, those that are irregular, transient, or just plain peculiar. These include moons that are more like asteroids, moons that come and go, or systems where moons share orbits in a celestial dance. The solar system has plenty of the strange along with the sublime, and in our next chapter, we shine a light on those lunar oddballs and mysteries. Oddballs and mysteries, irregular, ephemeral, and bizarre moons. Not all moons fit the mold of spherical worlds with stable, eternal orbits. The solar system is also populated with moons that are decidedly odd. Some are misshapen chunks, barely held together, looking more like asteroids than moons. Others follow peculiar paths or engage in orbital dances that seem to defy common patterns. A few are only temporary guests of their planets. These oddballs and enigmas highlight the playful creativity of gravity and the remnants of violent histories. First, consider shape. To be round, a moon needs enough gravity to pull itself into a sphere. Many moons, especially smaller ones, lack the mass for that, and instead have irregular, potato-like shapes. Mars's moons. Phobos and Deimos are classic examples. Phobos looks like a battered rock, pockmarked with craters, notably one giant crater that gives it a Death Star-like appearance. Deimos is smoother, having accumulated dust in its craters, but it's lumpy too. These moons are almost certainly captured asteroids, as their shape and composition suggest. They remind us that the line between moon and asteroid can blur. Around the giant planets, dozens of tiny moons likewise are irregular. Jupiter and Saturn each have swarms of little moons out beyond their big moons, often on eccentric or tilted, or even backward orbits. These are captured remnants from the early solar system or fragments of shattered moons. They typically have irregular shapes. Saturn's moon Hyperion is a standout. It's about 270 kilometers across and looks like a giant sponge. Hyperion's surface is bizarrely carved into deep pits, and its density is so low that scientists suspect it's a porous rubble pile that never compacted fully. To top its strangeness, Hyperion doesn't rotate steadily. It tumbles chaotically, its axis wobbling unpredictably due to gravitational perturbations from nearby Titan. If you tried to predict when the sun would rise on Hyperion for a given location, you'd have a hard time. Its spin is that irregular. Another irregularly shaped curiosity is Pan, a tiny moon of Saturn only 35 kilometers across. Pan orbits within Saturn's rings, in the Encke Gap, and has accumulated a skirt of ring particles around its equator, making it look like a flying saucer or a walnut. It has a bulging ridge, essentially a ring of its own, stuck to its equator. Atlas, another little ring moon, has a similar UFO-like look. These ridges likely formed as the moon scooped up dust and ice from Saturn's rings while orbiting within or near them. These mini-moons underscore how moons can shape and be shaped by their environment in surprising ways. Now, binary systems. While no planet besides Pluto truly has a binary moon system, where two moons orbit each other around a planet, Pluto and Charon deserve mention. Charon, roughly half Pluto's size, isn't just a moon. Together, Pluto and Charon act like a double dwarf planet system. They orbit a point in space between them, gracefully pirouetting around each other every 6.4 days, forever showing the same face to each other. This mutual tidal locking and the balance of sizes make Pluto-Charon a unique case in our solar system. It stretches the definition of moon, as one could argue Charon is not just orbiting Pluto, they orbit each other. If Earth's moon were a bit larger, Earth and the moon might similarly orbit a point in between. The Pluto-Charon example invites us to consider that in other solar systems, there might be exoplanets with moons so large that the distinction between planet and moon blurs, and they form true binary pairs. Within our solar system's moons, we also see co-orbital dances. Saturn's moons, Janus and Epimetheus, for example, share nearly the same orbit. They are only about 50 kilometers different in their orbital radius, and they race around Saturn in close pursuit. Every 4 years or so, the inner one catches up to the outer one, and they perform a gravitational do-si-do. They exchange energy and effectively swap orbits. The one that was inner moves to the slightly outer orbit, and the outer moves to the inner path. Then the cycle continues. It's a graceful swap that conserves momentum and prevents collision. For a long time, astronomers were confused by observations of what seemed like one moon in that orbit that occasionally jumped position, until they realized it was two. Another strange orbital choreography involves what we call Trojan moons. Two of Saturn's moons, Tethys and Dione, each have smaller moons that reside at the stable Lagrange points, leading or following the bigger moon by 60 degrees in the same orbit. Essentially, the little moons are locked in a gravitational sweet spot, shepherding the orbit of their larger partner. They're like captured attendants, forever preceding or trailing the larger moon. No other example of Trojan moons is known beyond Saturn, but the concept is intriguing. Moons of moons in stable configurations. Temporary moons are a particularly interesting category. Earth, besides our big moon, occasionally has other small mini-moons. These are tiny asteroids captured for a short time. For instance, in 2006, a small asteroid about a few meters in size was captured by Earth's gravity and orbited Earth for several months before drifting away. More recently, another mini-asteroid called 2020 CD3 was discovered orbiting Earth from 2018 until 2020. These temporary moons come and go, usually staying for a few orbits before the dynamics allow them to escape. They remind us that the definition of a moon can be fleeting. A moon can be there 1 year and gone the next. At any given time, Earth might have one or more tiny natural satellites temporarily, and we wouldn't know unless we look carefully with telescopes. Jupiter and other planets likely capture small asteroids on occasion too. Their hills of gravity are larger, but also their real estate is far from Earth, so we notice fewer of those captures. Retrograde moons and inclined oddballs add to the menagerie of strange. Many of the tiny outer moons of Jupiter, Saturn and Neptune orbit backward relative to the planet's rotation. Triton, again, is the largest retrograde moon, captured and forced to dance to Neptune's tune in reverse. These retrograde moons often have stretched, inclined orbits too, suggesting they were snared objects. There are also moons with remarkably eccentric orbits. One of Jupiter's distant moons, S2003J2, loops far out in an oval path, taking years to complete one orbit. Some small Saturnian moons oscillate in strange resonances, like Neptune's inner moons, Naiad and Thalassa. Naiad is in a slightly inclined oval path that bobs up and down in such a way that it avoids ever colliding with Thalassa, in what's been described as a dance of avoidance. Naiad laps Thalassa every few orbits, passing above or below it in a choreographed pattern dictated by resonance. Physical anomalies also intrigue us. Iapetus, Saturn's two-toned moon, aside from its dark light yin-yang coloration, boasts an equatorial ridge of mountains that wraps most of the way around like the seam of a walnut. How did such a ridge form? One theory is that Iapetus might have had a decaying ring of its own that collapsed onto its equator, building a chain of mountains. Or it could be the remnant of Iapetus's youthful spin, when it rotated so fast that the equator bulged and then froze in place as the moon cooled. It remains an odd and picturesque feature, unmatched elsewhere. And what about moons with rings? It sounds fanciful, but Saturn's second largest moon, Rhea, gave a hint of a possible ring system in some spacecraft data. If confirmed, that would be a moon with its own ring. As of now, it's an open question, and subsequent observations haven't clearly found rings around Rhea, so that mystery endures. These irregular, ephemeral, and surprising moons teach us that being a moon is not one size fits all. They are the exceptions that prove the rule, and sometimes they break the rules in delightful ways. They speak to the dynamic and often violent processes that populate planets with moons. Captures of passing objects, collisions that shatter a moon into pieces that become new moons or rings, gravitational tricks that allow multiple bodies to share orbits. They also show us how creative nature can be with orbits. As long as the laws of gravity are obeyed, seemingly odd arrangements can persist for millions of years. If you had an artist's eye, you might see Janus and Epimetheus as two dancers swapping positions on a giant stage, or the Trojan moon Telesto as forever surfing the gravitational wave ahead of Tethys. You might see Hyperion tumbling through space like a tossed sponge from the gods, never the same rotation twice, or Phobos slowly spiraling inward toward Mars, destined to either crash into the Martian surface or be torn into a ring in some millions of years. A moon in death throes, gradually succumbing to tidal forces. Yes, even the lifespans of moons can be finite. As mentioned, Triton will likely spiral into Neptune someday far off. Phobos is drawing closer to Mars by a few centimeters each year. Within 50 million years or so, it may break apart under Mars's tidal pull and possibly create a short-lived ring around Mars before raining down. Jupiter's intense gravity may eventually destabilize some of its captured shards as well. The temporary moonlets come and go on human timescales, hinting that the tapestry of moons is still being woven even now. Through these strange moons, we see the solar system not as a static set of clockwork orbs, but as an evolving, changing family with members that sometimes wander in, sometimes wander out, sometimes behave bizarrely. It's a cosmos of surprises. And as we prepare to send more explorers out there, who knows what other odd moons we might find? Perhaps a moon with active geysers of neon, colored chemicals, or a moon that is two halves barely held together, or moons in exotic resonant patterns yet unseen. We now have journeyed through nearly every aspect of moons, their mythic allure, their formation, their effects, their astonishing diversity and geology, and their curiosities. Our attention turns next to how we humans have stepped into this story with our machines and our own feet, through missions that have explored these moons, and how those missions have enriched our understanding and prepared us for even grander adventures to come. Reaching the moons, from Apollo to tomorrow's missions. Humanity's fascination with moons has not remained in the realm of observation and theory. We have boldly taken voyages to these distant worlds, sending spacecraft to uncover their secrets. Each mission, whether crude or robotic, has been a chapter in our unfolding understanding of moons, transforming points of light into real places with landscapes and histories. Let's journey through some of the landmark missions that have explored moons and look ahead to the missions on the horizon. The first tentative steps were robotic. In the late 1950s and 1960s, during the dawn of the space age, both superpowers, the United States and the Soviet Union, set their sights on Earth's moon. The Soviet lunar program achieved a series of historic firsts, the first human-made object to hit the moon, the first photos of the moon's far side, and later the first soft landing and the first robotic rover. These early missions proved the moon was reachable and prepared the way for something even bolder, landing humans there. In July 1969, the world watched in collective awe as Apollo 11 carried Neil Armstrong and Buzz Aldrin to the Sea of Tranquility. When Armstrong stepped off the lunar module's ladder, uttering, "That's one small step for a man, one giant leap for mankind," a dream as old as humanity was realized. The astronauts found a world of grey dust and rocks under a black sky, Earth hanging blue and bright above the horizon. Aldrin described the lunar landscape as magnificent desolation. Over the course of 6 Apollo missions, 12 humans walked on the moon, exploring different regions, driving a lunar rover across the soil, setting up experiments, and collecting rocks. These samples, returned to Earth, revolutionized lunar science. They told us the moon's composition, its volcanic past, and supported the giant impact theory by revealing the moon's similarity to Earth's mantle. Apollo 8, months before the landing, had already given us the iconic Earthrise photo, Earth rising over the moon's limb, an image that redefined how we see ourselves, a delicate blue marble in the vastness as witnessed from the moon. Apollo ended in 1972, and no human has been beyond low Earth orbit since, marking a pause in human moon exploration. But the legacy of Apollo lives on. In every reflective visor selfie an astronaut took on the moon, our planet is seen small behind them, a humbling perspective gifted to us by those missions. Even as Apollo ended, robotic explorers were gearing up to tour the outer solar system and its moons. In 1979, NASA's twin Voyager spacecraft flew past Jupiter and then Saturn. Voyager 1's cameras, as it swung by Jupiter, captured something astonishing. Active volcanoes on Io, the first proof of active volcanism beyond Earth. It was a discovery that made scientists gasp. Until that moment, we assumed moons would be cold and dead. Voyager also sent back tantalizing images of Europa's cracked ice shell and hints of complex surfaces on Ganymede and Callisto. At Saturn, Voyager 1 and 2 revealed Titan's thick, smoggy atmosphere and the spongy Hyperion, and many of Saturn's smaller moons in detail for the first time. These brief flybys were like flipping through a cosmic photo album, each image raising new questions. They paved the way for longer visits. In the 1990s, NASA's Galileo spacecraft became the first to orbit Jupiter. Galileo spent 8 years in the Jovian system, repeatedly flying by the Galilean moons. It confirmed that Europa likely harbors an ocean beneath its ice, photographed Europa's ridges and chaotic terrains up close, and even saw what looked like rafts of ice that had broken and shifted. Galileo also found evidence that Ganymede has its own magnetic field, and hinted that Callisto might have a subsurface ocean too. Meanwhile, Galileo watched Io's volcanoes in action, seeing plumes and red glowing lava, and mapped the resulting changes. This extended exploration turned those moons from curiosities into richly studied worlds. Galileo, however, suffered a stuck antenna, which limited the data return, yet still transformed our understanding of Jupiter's moons. Around the same time, attention turned back to Saturn. The Cassini-Huygens mission, a collaboration between NASA, ESA, and others, launched in 1997 and arrived at Saturn in 2004. For 13 years, Cassini orbited Saturn, a marvel of longevity and discovery. It carried a passenger, the Huygens probe, which in 2005 descended through Titan's atmosphere and landed on Titan's surface, the first landing on a moon beyond our own. Huygens sent back images from beneath Titan's orange sky, rounded icy rocks, a damp riverbed, and a horizon shrouded in fog. It was like standing on a primordial Earth, bitterly cold and alien, yet eerily familiar in geomorphology. Cassini, orbiting above, mapped Titan's surface with radar. revealing lakes and dunes, and it watched Titan's seasons change over the years. Cassini's tour of Saturn's moons was like a grand saga. It discovered the water plumes of Enceladus, flying through them to taste their composition. It imaged Enceladus's tiger stripes in detail and confirmed an ocean beneath its ice. It photographed Iapetus's two-tone divide and dramatic ridge, investigated Hyperion's chaotic tumble, saw jets off tiny moon Daphnis sculpting Saturn's rings, and even witnessed a meteorite crash into Saturn's rings, a tiny collision caught serendipitously. Cassini made hundreds of flybys of Saturn's moons, essentially writing the textbook on the Saturnian system. When Cassini's fuel grew low, NASA chose to end the mission by plunging Cassini into Saturn in 2017. In its final orbits, Cassini gave us unprecedented close-ups of the rings and measurements of Saturn's gravity, a fiery grand finale for an epic mission. As it disintegrated in Saturn's atmosphere, scientists and the public alike bid farewell to a venerable explorer that had, quite literally, broadened our horizons. After Cassini and Galileo, our explorations continued. New horizons flew by Pluto and Charon in 2015, revealing the surface of Charon, the moon half of that binary, in detail for the first time. Pluto's heart and mountains stole the show, but Charon's discovery of a giant chasm and a dark reddish cap of tholins at its pole added to the list of surprising moon geology. Even Neptune's moon Triton got another look, albeit distantly, with Voyager 2. We haven't returned since, but proposals exist to send an orbiter there in the future. Meanwhile, back to Earth's neighborhood, our moon saw renewed robotic visitors. Orbiters like NASA's Lunar Reconnaissance Orbiter, mapping it in high definition, and China's Chang'e program achieving soft landings, including on the far side. These missions found water ice in permanently shadowed craters at the lunar poles, a valuable resource for future explorers. They also continue scientific investigations of lunar geology and even biology experiments. Now we stand on the brink of a new wave of exploration, the era of returning to the moon and pushing farther to the outer moons with advanced probes. NASA's Artemis program is the flagship of human spaceflight in this realm. Named after Apollo's twin sister, Artemis aims to land the next man and the first woman on the moon, focusing on the lunar South Pole region where water ice resides in shadowed craters. Artemis I, an uncrewed test flight of the mighty Space Launch System rocket and Orion spacecraft, flew around the moon in 2022, heralding the return of NASA's crew, capable deep space vehicles. Artemis II will carry astronauts on a lunar flyby, and Artemis III, slated for the mid-2020s, hopes to put boots on lunar soil again. The plan is not just flags and footprints this time, but to establish a sustainable presence, perhaps a lunar base or the lunar gateway, to facilitate ongoing exploration. Living and working on the moon will serve as a testbed for eventual human missions to Mars. One can imagine future astronauts at the moon's south pole, sunlight skimming the horizon as they harvest ice for water and fuel, and look up to see the distant blue Earth and perhaps beyond it, glints of Jupiter or Saturn, moons gazing upon other moons. On the robotic front, one of the most anticipated missions is NASA's Europa Clipper, set to launch in the mid-2020s. This large spacecraft will orbit Jupiter and make dozens of close flybys of Europa, scanning its ice shell with radar, measuring its magnetic field to confirm the ocean's characteristics, imaging the surface at high resolution, and sniffing for any signs of plumes or organic molecules. Europa Clipper's goal is to assess Europa's habitability, essential groundwork, if we ever decide to drill through that ice or send a submarine into its ocean. Around the same time, the European Space Agency's JUICE mission, launched in 2023, is on its way. By 2030, JUICE will arrive at Jupiter and focus on Ganymede, while also studying Europa and Callisto in flybys. JUICE will give us an unprecedented look at Ganymede's magnetic field, its suspected ocean and surface. Looking further ahead, concepts are being studied for an Enceladus mission that would orbit or land on this tiny moon to directly search for signs of life, perhaps by sampling fresh plume material for complex organic compounds or even cell-like structures. Another mission, Dragonfly, is in development to go to Titan. This one a rotorcraft lander that will launch in 2027 and arrive in the mid-2030s. Dragonfly will hop between different sites on Titan's surface, investigating the chemistry of its dunes and possibly the edges of its methane seas in search of prebiotic chemistry or even biosignatures, and to understand Titan's chemistry. Meanwhile, the Japanese Space Agency is preparing the Martian moon's exploration mission to Phobos. Scheduled to launch in the mid-2020s, MMX will land on Mars's moon Phobos, collect samples, and return them to Earth, aiming to reveal that moon's origins. Every mission to a moon brings new wonders. Cassini's findings of Enceladus's habitable ocean were not even on the radar when Cassini launched. We were taken completely by surprise. What surprises might Europa Clipper or Dragonfly or Artemis astronauts have in store? Perhaps plumes on Europa will reveal organic molecules more complex than any found off Earth so far. Perhaps Dragonfly will find that Titan's organic soup has formed something like primitive cell membranes or interesting electrical patterns in the hydrocarbon lakes. Maybe Artemis explorers will discover a new mineral in the lunar craters, or even microbial life hitchhiking from Earth that survived in lunar ice, giving cautionary data for planetary protection. These missions are not just about satisfying curiosity, they carry profound implications. If a future probe finds even microbial life on another moon, it would prove that life is not unique to Earth. If we find an absence of life in places that seem habitable, that too tells us something, that life might be rarer than we assume or needs more specific circumstances. Human missions like Artemis aim to make the moon a part of humanity's sphere, no longer an unattainable orb, but a place where people can work, research, and perhaps one day even mine resources or build observatories. There's also an emotional and cultural resonance to these explorations. Apollo's pale suits against grey dust became an icon of the 20th century. The image of Huygens landing on Titan, navigating by parachute down through orange clouds, fired imaginations about exploring alien skies. Each mission extends our senses. With cameras, we have stood on the slopes of mysterious mountains on the moon and looked back at Earth. We have floated above Jupiter's swirling storms, with Io glowing in the foreground. We have watched a sunset on Titan through a hazy atmosphere. We voyage through our probes, living vicariously through their lens. As we continue to reach out, it's worth remembering that these endeavors are also acts of stewardship of knowledge. We learn not just about those moons, but about Earth by comparison, about how planets and moons interact. And these missions inspire generations. Some who watched Apollo or Voyager are today the ones designing Artemis and Europa Clipper. Our expedition through the history and future of moon exploration underscores a theme. Once unreachable, moons are now within our grasp. We have touched our moon, orbited others, and landed on a few. We have plans to return and even reside for a while. Robotic envoys will soon sniff the air of distant moons and crawl on their surfaces. It's an exhilarating time, blending the spirit of adventure with meticulous science. Equipped with all this knowledge and experience, our perspective shifts when we look up at the night sky now. We don't just see a bright moon, we see a place humans have stood and will stand again. We spot Jupiter as a point of light and imagine the pinpricks of Io's volcanoes or Europa's potential plumes. Saturn's golden dot brings to mind the lakes of Titan and the geysers of Enceladus. These celestial lights have become places in our minds. With our machines and dreams, we have brought the solar system's moons into our realm of experience, if not physical, then intellectual. And with each mission, we become a species not confined to one world, but a bit more at home in the vast archipelago of worlds that orbits our sun. Now, beyond our sun, countless other stars shine in the night. Around many of those stars orbit planets, and around some of those planets, perhaps moons. Before concluding our journey, let us cast our gaze even farther, to the possibility of moons circling distant exoplanets, and consider what their existence might mean. Moons beyond our solar system, the quest for exomoons. So far, our tale has stayed within the bounds of our sun's family. But even as we explored the moons of our solar system, astronomers have been pondering a tantalizing question. Do moons exist around planets of other stars? We call such hypothetical worlds exomoons, and finding them is an ongoing quest at the cutting edge of astronomy. If planets are common in the galaxy, it stands to reason that many of those planets, especially the giant ones, should have moons. Perhaps some alien sky has a view as lovely as Jupiter and its retinue. Or perhaps an Earth, like exomoon, orbits a huge planet in a distant star's habitable zone, providing a home for life. Detecting exomoons is, however, even more challenging than detecting exoplanets. Planets themselves often are found indirectly, for example, when they transit their star and cause a tiny dimming of starlight, or when their gravity makes a star wobble. A moon is smaller still, and its effects subtler. Nonetheless, scientists have devised clever ways to hunt for them. One method is to look for slight irregularities in a planet's transit timing or duration. An unseen moon tugging on the planet could cause it to wobble and transit a bit early or late, or produce extra dips in starlight. Another approach is direct imaging. A few large exoplanets have been photographed around stars. A sufficiently large and well-separated moon might one day be directly observed in such images. In 2018, researchers announced the first compelling exomoon candidate. Using data from the Kepler Space Telescope, they studied a Jupiter-sized exoplanet called Kepler 1625b, around 8,000 light-years away. They noticed hints that this planet's transit was followed by a smaller dip, possibly a Neptune-sized moon trailing the planet. Follow-up observations with the Hubble telescope added evidence that something was there, although the result remains unconfirmed and debated. If real, this exomoon would be far larger relative to its planet than any in our solar system, a reminder that exoplanets continue to surprise us with their diversity. In 2022, another possible exomoon was reported, also quite large, though it too awaits confirmation. Why the focus on giant moons? Simply because our current techniques are sensitive enough only to detect very large moons, likely gaseous or icy, around big planets. We don't yet have the capability to find an exomoon akin to our moon around a distant Earth-like planet. But as technology improves, through new space telescopes and more sensitive instruments, astronomers hope to eventually detect smaller exomoons, perhaps even down to the size of Mars or Earth. The implications of exomoons are exciting. Some scientists argue that an Earth-sized moon orbiting a gas giant in the habitable zone of a star could be a habitable world itself, essentially a moon planet with conditions for life. This scenario, reminiscent of science fiction locales like the forest moon of Endor in Star Wars, is scientifically plausible. A large moon could have an atmosphere, liquid water, and stable environments, all while orbiting a protective big planet. The presence of a giant planet could even shield the moon from excessive asteroid impacts or provide a magnetic field umbrella. On the other hand, it might also bathe the moon in radiation, posing challenges for life on the surface, but perhaps life could thrive underground or underwater. Exomoons also broaden our perspective on where life might arise. We now know to look not just at planets, but their moons. In our solar system, we see potentially life-friendly environments on moons like Europa and Enceladus. If similar moons exist elsewhere, the galaxy's habitable real estate could be significantly expanded. A star's habitable zone might contain giant planets that themselves are inhospitable gas balls, but their moons could be the true gems. The search for exomoons is a testament to our desire to not only find analogues of our planet, but also analogues of our moon and the rich relationships that moons have with their primaries. It forces us to refine techniques and maybe even build future observatories dedicated to this faint whisper of a signal. Perhaps in the coming decades, we will get our first confirmed detection of an exomoon. And if we are truly fortunate, one day we might even glean information about its atmosphere or composition, enough to say, for instance, this moon has oceans and clouds. The existence of exomoons, confirmed or not, also has a philosophical tinge. It underscores that our solar system is not unique in its complexity. The dance of planets and moons is likely a common cosmic theme. Somewhere out there are moons that cause eclipses as seen from their planets' surfaces, moons that tug tides on alien oceans, moons that might glow with bioluminescent life under foreign skies. We have begun to suspect their presence. The next generation of telescopes will no doubt reveal them one by one. When we finally do find them, exomoons will become part of our ever-expanding narrative of the cosmos. Each new moon discovered around a distant sun will be a reminder that nature's creativity is boundless. The moonlit nights we know on Earth, so special to us, might be a universal experience shared under many skies. And knowing that adds a profound connection. The same way every human culture under our moon found meaning in its glow, perhaps across the galaxy, other beings dance under the light of their moons. For now, exomoons remain a frontier, a promising echo of the familiar in the vast unknown. As our documentary journey transitions from exploring the known moons to reflecting on their meaning, the possibility of exomoons serves as a bridge. It links the concrete knowledge we have gained about moons in our solar system with the tantalizing potential of worlds yet to be discovered, out beyond our reach, but not beyond our imagination. Reflections. Under alien moons, meaning and metaphor. Throughout history, the moon has been a mirror, not just of sunlight, but of human thought and emotion. We have cast our dreams, fears, and philosophies onto that gentle disk in the night. Now, having journeyed among the moons of the solar system, we return with a richer tapestry of meaning. We see that every moon, in its own way, is a symbol, and their stories resonate with our own. From our earliest days, the moon was a companion in the dark, a source of wonder and reassurance. It waxed and waned, teaching us about cycles, the idea that endings are not final, for the crescent grows again after the new moon's darkness. In this, people found hope and rhythm. The moon became associated with the cyclical nature of life, time measured in moons, the tide, like flow of fortunes, the rhythms of fertility and growth. Poets compared the waxing moon to a growing child or the blossoming of love, and the waning moon to aging or heartbreak, yet promised renewal in the next cycle. Nearly every culture saw something personal in the moon's face. Some saw a compassionate figure, a goddess who lights the night and watches over lovers and lost travelers. Others saw a clever god, or a mischievous rabbit, or a reminder of heroic stories. These myths, diverse as they are, share a sense of the moon as an object of connection between the heavens and human hearts. The moon was distant, yet felt intimately close, influencing daily life through calendars and tides, and nightly life through its calming glow. It symbolized the known in the unknown, a gentle light amidst darkness. Now consider our new knowledge. Moons are everywhere, not just orbiting Earth. Each planet has its own moonlight in its sky, its own tidal rhythms imposed by orbiting companions. The idea that moons are silent watchers extends beyond Earth. One can imagine a hypothetical being on Jupiter's cloud tops marveling at the dance of Io and Europa, or a being on Titan witnessing Saturn's rings casting shadows in Titan's sky, with tiny Enceladus sparkling as a star like point. The presence of moons is a universal feature of planetary systems, which suggests something profound. The concept of a smaller body, forever bound to a larger one, is a motif written into the cosmos. It invites metaphor. Are we not all, in some sense, moons? We live our lives influenced by greater forces, the gravity of our communities, our nations, our planet, the sun's energy, the pull of tradition and history. Yet within those orbits, we have our own trajectories, our own landscapes and individuality. To be a moon is to be a follower, a companion. But our exploration has shown that a companion world is still a world. Being gravitationally bound to a planet doesn't diminish a moon's uniqueness. In fact, that relationship can enrich it. Tidal heating can endow it with fire and ocean. Tidal locking gives it a permanent sky view of its primary and perhaps a special stability. In the same way, perhaps being bound to greater things, family, society, the earth itself, does not diminish individuality, but provides context that allows life and meaning to flourish. Moons, by their very existence, teach a lesson of belonging. No moon floats alone in space. Each is part of a system, just as we are all part of something larger, be it family, culture, or the biosphere. And yet, moons also teach resilience and identity. Think of Triton, captured against its will, retrograde and rebellious, yet it settled and became one of the most intriguing moons we know, forging geysers under Neptune's distant sunlight. Or Europa and Enceladus, tiny in comparison to their planets, yet possibly cradling more life potential in their hidden seas than the huge worlds they orbit. Size and rank do not correlate with significance. A small moon can have a global ocean. A giant planet might be a sterile gas ball. Likewise, a single human or small community can harbor creativity, love, and innovation that influence the larger world profoundly. The relationship is symbiotic. The big influences the small, and the small can influence the big. The moon has also always symbolized reflection. It shines, but with borrowed light. In that, there is a deep metaphor. We too shine often with light passed to us by others, knowledge, wisdom, kindness that we have received, and then reflect onwards. Our ideas are illuminated by the great thinkers before us. Our compassion is lit by the love we've been shown. And like the moon, which can cast enough light to show the way in darkness, we too can reflect the light of greater truths or greater goodness into the dark corners of each other's lives. We might also think of the moon as representing the idea of being secondary, yet essential. Planets dominate their moons in gravity, but if you remove the moon, the system changes drastically. Earth without its moon might not have fostered such stable, life-friendly conditions. Jupiter, without its Galilean moons, would lack the most interesting aspects of its identity. In the same way, what orbits around a person or a society, its art, its ideas, its satellites of influence, though secondary in mass or power, might be what truly defines it. A planet without moons is a bit like a leader without companions or a mind without dreams, functional but missing depth and nuance. Consider also the perspective of standing on a moon looking up at its planet. On the moon, astronauts gazed up and saw Earth, a swirling orb of blues and whites, a sight that moved them to profound introspection. On Io or Europa, one would see Jupiter's banded enormity filling the sky, a constant reminder of a bigger presence. Perhaps this is akin to moments in human life when we stand in awe of something larger than ourselves, standing before the vast ocean or a towering mountain, or contemplating the galaxy on a starry night. We feel small, yet connected to something grand. Moons literally live with that view every day. They know, if one can poetically assign knowledge to them, what it means to always circle something awe-inspiring and bigger. But they also show that one can have one's own identity in that situation. The people of ancient times could look at the moon and feel both the greatness of the heavens and the personal comfort of that lantern in the sky. There's a balance there of humility and significance. Culturally, the moon often symbolizes the subconscious or the hidden, as the sun symbolizes the obvious and conscious. The moon comes out when the sun leaves, revealing stars, hinting at mysteries. Likewise, exploring the moons of the solar system has been an exercise in illuminating the previously unseen, delving into the mysteries of how diverse nature can be and holding a mirror to our assumptions. Who would have expected that desolate-looking Europa would hide a deep ocean, or that tiny Enceladus would shoot geysers into space, visible to Cassini's cameras? These discoveries were like subconscious truths emerging, showing that reality is richer than daylight logic might predict. We, as a species, are enriched by these revelations. They remind us to keep an open mind and appreciate the unseen forces and potentials in our own lives and world. The phrase orbiting something greater resonates beyond astronomy. Philosophically, it speaks to a relationship between part and whole, self and other, finite and infinite. We on Earth orbit the sun, a star that gives us life. The sun orbits the center of the galaxy. Perhaps even galaxies orbit some center in a cosmic dance. At every scale, orbiting something greater is the rule. It does not diminish the smaller. Instead, it binds systems together in a dynamic balance. One could poeticize that electrons orbit atomic nuclei, and in doing so, create the atoms that build everything tangible. It's orbiting that allows structure, so being in orbit is not a subservient act. It's a creative one that allows complex structures and stability. Without orbiting, without relationships of gravitation and revolution, the universe would be a diffuse, structureless haze. Likewise, in human existence, binding oneself to ideals, causes, or communities greater than oneself can give structure and meaning to life. We orbit principles of justice, love, or curiosity, and that orbit guides us and gives our journey shape. Standing under the night sky now, we no longer see moons as mere lights or dots. We see destinations that humans and our robotic envoys have touched. We also see stories. The moon is no longer just Apollo's goal, but Artemis's next foothold, and a muse for humanity's future. The moons of Jupiter are no longer just Galileo's tiny points. They are volcanic Io, oceanic Europa, massive Ganymede, ancient Callisto, each a world to marvel. We are connected to them now by knowledge and by the anticipation of discovery. When we behold Saturn through a telescope and spot Titan as a faint dot, we know there's an Earth-like sky there, and perhaps we feel a kinship with whatever chemistry is brewing on its surface. In a sense, through exploration, all these moons have become extensions of our mental world. Our human story has expanded to include them. We've left footprints on one, tire tracks on another, probe markings on Titan's frozen ground. We've made these distant places, in some measure, part of our shared human experience. And as we did so, we found that those places were not barren in meaning. They reciprocated by teaching us about ourselves. They taught us patience, taught us humility, taught us unity. In mythology, the moon often represented the feminine, the cyclical, the responsive, complementing the sun's masculine, steady output in many cultures. One could say the moons of the solar system collectively represent the yin to the planet's yang, the supportive, nurturing side of planetary systems. They stir tides. They may nurture life in their oceans. They moderate axes and climates. And philosophically, maybe we as humanity play a moon-like role in relation to our planet, nurturing it by reflecting the light of knowledge and awareness onto it. We have the power to bring unconscious processes into consciousness and address them, much as the moon's light allows us to navigate the dark. Finally, consider the sheer beauty and improbability of it all. In a universe that may be mostly empty, here we are in a system with a wealth of moons, where one tiny rocky sphere can orbit a gas giant and harbor a subsurface sea that might host alien microbes. Or where a dead-looking moon turns out to have cryovolcanoes that paint its surface. Is this not wondrous? It speaks to an inherent creativity in nature. In that, some find spiritual meaning, seeing in the proliferation of moons and their diverse stories a sort of cosmic art, an expression of what some might call the divine, or simply the boundless creativity of physics. The moons invite us to think about companionship and solitude. Our Earth's moon has been a constant companion, night after night. Mars's little moons accompany it like faithful, if odd, shaped pets. Jupiter carries an entire miniature solar system, a reminder that even in the company of others, each member can be distinct and vital. As we humans venture out, possibly one day establishing bases on the moon or visiting Mars, we too become companions to these moons, integrating ourselves into the cosmic neighborhood as participants, not mere observers. In closing our journey, we return to a simple scene, a person standing under a moonlit sky, gazing upward. Beyond the silhouette of our moon, our mind's eye knows there are other moons orbiting distant planets, shining in their skies. The night is richer now. We feel connected to something far beyond, as well as deeply rooted in our own world. The silent watchers of the night have shared with us their stories, and we find that they are our stories too. Stories of orbit and influence, of reflection and yearning. In their silent orbits, these moons, great and small, are indeed guardians of the night. They keep the stories of their planets and share their light with the darkness. As our journey ends, we look up with a deeper reverence. The night sky is alive with these silent companions, forever circling, forever reflecting. They inspire us to continue our cosmic dance of exploration, and under their watchful glow, we carry onward, seeking knowledge, seeking connection, and seeking our place among the stars. We look up on a clear night and see thousands of tiny lights sprinkled across the sky. From ancient times to the present, people have been captivated by the stars. They have inspired wonder, guided travelers, and sparked countless myths and legends. Humans imagined patterns in them and told stories about gods, heroes, and animals in the heavens. We use the stars to navigate oceans and to mark the seasons. But what are these brilliant pinpricks of light really? Stars are giant, luminous balls of plasma, held together by their own gravity and powered by nuclear fusion at their cores. In simple terms, a star is a colossal nuclear furnace in space, constantly fusing lighter elements into heavier ones and releasing tremendous energy as light and heat. They seem eternal and unchanging to us, but in reality, stars are born, they age, and they die, undergoing dramatic changes over millions or billions of years. Our sun is one such star. In fact, it's the only star close enough for us to feel its warmth and light directly, and it's just one among an uncountable multitude of stars in the universe, each with its own story. Now, imagine journeying into a vast cosmic cloud far out in space, where new stars are born. These regions are called nebulae, enormous, diffuse nurseries of gas and dust, sprinkled throughout the galaxies. They are the cradles of star formation. If you could float inside one, you might see faint, ghostly glows and dark, opaque patches where starlight from outside is blocked. The famous pillars of creation. Photograph of the Eagle Nebula, for instance, shows towering columns of gas and dust rising like mountainous spires. Within those cold, shadowy pillars, new stars are slowly taking shape. The Great Orion Nebula, visible as a faint smudge in Orion's sword, is one such stellar nursery, a cavern of gas and dust over 20 light-years wide, where thousands of baby stars are forming. Here, in the cold, dark depths of a nebula, the story of a star begins. A slight nudge, perhaps the shockwave from a distant supernova or a random density fluctuation, causes parts of the cloud to begin collapsing under their own gravity. Over thousands to millions of years, a portion of the nebula's gas gathers more and more mass, pulling in surrounding material. As this pocket of gas shrinks, it grows denser and hotter, and it starts to spin faster. Eventually, it forms a growing ball of gas known as a protostar, a baby star that's still gathering mass. Surrounding it, a flat disk of gas and dust often forms, whirling around the protostar. Protostars also often fire out bipolar jets, narrow beams of gas blasting out from their north and south poles. These high-speed jets can plow through the surrounding nebula, creating glowing shockwaves and carving cavities in the cloud. The protostar at the center continues to contract and heat up as gravity relentlessly squeezes it. Deep in the core of this protostar, temperatures climb into the millions of degrees. The gas is mostly hydrogen, the simplest and lightest element. When the core temperature reaches roughly 15 million degrees Celsius, something miraculous happens: ignition. Hydrogen nuclei begin to fuse together to form helium, unleashing a tremendous amount of energy. This is the moment a star is truly born. The protostar has become a full-fledged star, blazing with its own light. The once dark core suddenly glows brilliantly, and the outward pressure of this new energy release halts the gas collapse. The infant star turns on, so to speak, and starts shining. The surrounding cocoon of leftover gas and dust gets blown away by the fierce stellar winds and radiation now pouring from the newborn star. The star stabilizes, no longer contracting, as a balance is struck. It has entered the long, stable phase of its life, known as the main sequence. Often, stars do not form alone. Many newborn stars come in groups called star clusters. Our Sun likely formed in a cluster with several sibling stars, which have since drifted away. Once nuclear fusion starts in the core, a star finds an equilibrium. Outward pressure from the fusion energy balances the inward pull of gravity, and the star stops shrinking. It becomes stable, neither collapsing nor exploding, steadily glowing. The star will remain in this state, fusing hydrogen in its core, for the vast majority of its lifetime. It's as if the stellar engine is idling at a steady rate. This newfound stability allows the star to shine consistently for a very long time. Millions, even billions of years will pass with the star in this tranquil main sequence phase. Our Sun is in fact in this phase right now, and has been for about 4.6 billion years. This stability is fortunate for us. It means the Sun's energy has been steady enough to allow life to develop on Earth, and will continue for eons more. If our Sun were a short-lived massive star, life as we know it might never have had the chance to arise in the brief stellar lifetime. Main, sequence stars like the Sun quietly convert hydrogen to helium, radiating energy into space and providing warmth and light to any orbiting planets. In this main sequence stage, a star shines by nuclear fusion, fusing hydrogen atoms into helium in its core, and in doing so, it releases an absolutely colossal amount of energy. To give a sense of scale, our Sun fuses about 600 million tons of hydrogen every second, turning it into about 596 million tons of helium. The missing mass, roughly 4 million tons per second, is converted to pure energy according to Einstein's famous equation E=mc2. 4 million tons of matter turned into energy every single second. This energy then radiates outward from the core, through the Sun's layers, and eventually into space as heat and light. The numbers are mind-boggling. The Sun's energy output each second is about 3.8 × 10⁻²⁶ watts, a figure almost impossible to imagine. To put it in human terms, the power the Sun releases every second is equivalent to the energy from billions of nuclear bombs exploding at once. Yet this gargantuan output has been running continuously for billions of years, and will continue for billions more. It's sobering to realize that for most of human history, the source of the Sun's power was a mystery. Only in the 20th century did scientists like Arthur Eddington and Hans Bethe figure out that nuclear fusion is what makes the stars shine. Millions of such stars fill our galaxy, each a massive energy source blazing in space. Not all stars are like our Sun, however. Stars come in a stunning variety of sizes, colors, and luminosities. Some are far bigger and hotter than the Sun, shining blue, white, and piercingly bright. Others are smaller and cooler, glowing a faint red. The color of a star is a clue to its surface temperature. Hotter stars emit more blue, white light. Cooler stars more red, orange light. For example, in the constellation Orion, you can spot a contrast between the supergiant star Betelgeuse, which shines with a reddish hue, and Rigel, which gleams bluish-white. In general, a blue star might be tens of thousands of degrees at its surface, while a red star might be only a few thousand degrees. These differences correspond to spectral classes. Another example, the star Sirius, the brightest star in Earth's night sky, is about twice the Sun's mass and has a surface temperature of around 9,400 K, giving it a white-blue sparkle. On the other hand, our Sun is yellow, white, and a typical small red dwarf star would look deep red to our eyes. The vast majority of stars in our galaxy are actually small, cool red dwarfs. Perhaps 70–80% of all stars fall into this category. These red dwarfs are so dim that not a single one is visible without a telescope. In fact, the smallest true star ever measured is only slightly larger than the planet Saturn. With just about 8% of the Sun's mass, it barely manages to sustain fusion. Were it any smaller, it would fail to ignite and become a failed star, known as a brown dwarf. By contrast, most of the stars we see sparkling in the night sky are the larger, more luminous types that, while much rarer, shine hundreds or thousands of times brighter than red dwarfs and can be seen across great distances. If you stood on a hypothetical planet orbiting a red dwarf, the star might hang in a dim red sky, casting an eerie dusk, like light even at noon. By contrast, a planet around a hot blue-white star would be flooded with a stark, bluish illumination and intense ultraviolet rays. Size and mass have a profound effect on a star's fate. In general, the more massive a star, the hotter and brighter it burns, and the shorter its life. A star 10 times more massive than the Sun might emit thousands of times more energy, blazing a brilliant blue, white, but it will use up its fuel at an unsustainable rate. It's the difference between a gas, guzzling sports car and an economy car. The massive star burns through its fuel quickly, while a small star is extremely fuel efficient. Massive stars live fast and die young in a cosmic sense. Such a star might last only a few million years before it exhausts its core fuel. In contrast, a tiny red dwarf sips its hydrogen fuel so slowly that it can continue burning for hundreds of billions or even trillions of years. To put it in perspective, the universe itself is about 13.8 billion years old, so no red dwarf has had time to even come close to dying yet. Our Sun lies somewhere in the middle of the mass range. It's a G-type yellow dwarf, not exceptionally massive or small. It will have a total lifetime of roughly 10 billion years, moderately long by stellar standards. So far, the Sun has been shining for about 4.6 billion years, and it has about 5 billion to go before it starts to run out of core hydrogen. Because of these lifespan differences, no red dwarf star has ever died in the history of the universe. The universe simply hasn't been around long enough for the smallest, slowest, burning stars to use up their fuel. Even the oldest red dwarfs, born shortly after the Big Bang, are still shining today and will keep on shining for trillions of years to come. By the far distant future, long after bigger stars like the Sun have died, red dwarfs will be the last stars remaining, quietly glowing red in a fading universe. On the other end of the spectrum, many massive stars have lived and died in that same time, blazing through their fuel in a few million years and ending in catastrophic explosions. In a sense, the cosmos has a way of favoring the slow and steady when it comes to longevity. Eventually, even the most long-lived star will run low on fuel. When a star has fused most of the hydrogen in its core into helium, it starts to leave the stable phase of its life. The delicate balance that maintained the star for so long begins to falter. With less nuclear energy being produced in the core, the outward pressure that held the star up drops. The core, now largely helium, begins to contract under gravity since nothing is pushing back as strongly. And when the core of the star contracts, surprising things happen in the layers around it. The contracting core heats up a lot. This intense heat radiates into the surrounding shell of hydrogen that wasn't previously hot enough to fuse. Now that shell of hydrogen does begin fusion. So hydrogen fusion essentially migrates from the core to a shell around the core. Meanwhile, the helium core will eventually get hot enough to ignite a new kind of fusion. It will start fusing helium into carbon. The star's internal structure rearranges: a small, dense, very hot core fusing helium, and a shell around it fusing hydrogen. All this generates a tremendous amount of energy in the star's interior. The result is that the outer layers of the star are pushed outward, far outward. The star balloons in size. As the surface expands, it cools. The once yellow-white star becomes a cooler red star. It has now become a red giant. The term is literal. It is redder in color and gigantic in size compared to before. A star in this phase can swell to tens or even hundreds of times its original diameter. One day, about 5 or 6 billion years from now, our sun will undergo this transformation into a red giant phase. As it approaches old age, it will exhaust the hydrogen in its core and begin fusing helium. The sun's core will contract and heat up, and its outer layers will expand dramatically. In the process, the sun's radius will likely grow so large that it engulfs Mercury and Venus, the two innermost planets, and comes perilously close to Earth's orbit. From Earth's perspective, the sun would swell to an enormous red orb dominating the sky. The temperature on our planet would skyrocket. In fact, long before the sun's surface actually reaches Earth, the intense heat will boil away Earth's oceans and atmosphere and render our planet uninhabitable. Essentially, a scorched, lifeless rock. There is a chance Earth might be swallowed up entirely by the sun's expanded atmosphere, or it might just survive, parched and baked. Either way, the inner solar system will be unrecognizable. The sun will not only grow in size, it will also lose a lot of its mass via a powerful stellar wind. With less mass, the sun's gravitational pull on the remaining planets will weaken, causing those planets to drift outward to wider orbits. This red giant phase is a dramatic change, but fortunately for us, it's billions of years away in the future. For a star of the sun's mass, this red giant stage is essentially the beginning of the end. After perhaps 1 billion years in the red giant phase, the sun's core will have fused its helium into carbon and oxygen. It won't be hot enough to fuse those heavier elements, so the core will remain as a hot ball of carbon and oxygen. Without new fusion to support it, the core will contract further, and the outer layers of the sun, which expanded so far out, will become increasingly unstable. In a series of pulses, those outer layers will be expelled into space, creating a brilliant cloud of gas around the dying star. This glowing shell of ejected gas is called a planetary nebula. The sun, in its death throes, will thus cast off its atmosphere, which will drift away as an expanding bubble of gas. Planetary nebulae can be stunningly beautiful. Observed through telescopes, they appear as multicolored rings or shapes of glowing gas. In a few tens of thousands of years, the sun's shed gases will mix into the interstellar medium, enriching it with elements the sun made. All that remains of the sun at this point will be its former core. This exposed core is a hot, extremely dense orb about the size of Earth. It's called a white dwarf, the final state of a low to mid-mass star like our sun. A white dwarf no longer has fusion happening in its center. It is supported against further collapse by quantum pressure. It is, essentially, a stellar ember, an extremely hot cinder left over from the star's life. When it first forms, a white dwarf is incredibly hot and glowing white, blue, but it's also very small, so its total light is relatively faint. Over billions of years, it will cool and fade. To appreciate just how dense a white dwarf is, it packs roughly the mass of the Sun into a volume the size of Earth. Imagine compressing something as massive as a star into a ball only 8,000 miles across. The density of such an object is mind-boggling, on average about 1 million times denser than water, meaning a single cubic centimeter of white dwarf material would weigh on the order of 1 ton. In other words, a teaspoon of white dwarf matter would weigh several tons here on Earth. The gravity on its surface would be hundreds of thousands of times stronger than Earth's. If you somehow stood on a white dwarf, you would feel yourself weighing so much that you'd be crushed instantly. Over a very, very long time, a white dwarf will radiate away its heat and cool down. Eventually, after many tens or hundreds of billions of years, it would become a black dwarf, essentially a cold, dark, stellar remnant. In the case of our Sun, this is its ultimate fate, to spend eternity as a faint, white, hot star gradually cooling into darkness. Indeed, most stars end their lives quietly as white dwarfs, simply cooling and fading away. Only the most massive stars end in the spectacular supernova route. Now consider a star much more massive than the Sun, say a star born with 10 or 20 times the Sun's mass, or even more. These stars go through their lives much more quickly and violently. They too will leave the main sequence once their core hydrogen is exhausted, but the sequence of events is even more extreme. Such a star becomes a red supergiant instead of a mere giant. One of the best known examples of a red supergiant is Betelgeuse, the bright reddish star in Orion's shoulder. Betelgeuse is about 15,020 times as massive as the Sun and has expanded to a tremendous size. Observations estimate it is on the order of 700–800 times the Sun's radius. If Betelgeuse were placed at the center of our solar system, it would extend well past the orbit of Mars and possibly even approach Jupiter's orbit. It's so large that its volume would encompass tens of millions of suns. And Betelgeuse isn't even the largest star known. A few rare hypergiant stars, such as UY Scuti or Stephenson 218, are believed to have radii around 1,500 × 2,000 times that of the Sun. Truly monstrous stars. These colossal stars are extremely luminous and short-lived. Betelgeuse, for instance, is only on the order of 10 million years old, yet it is already in its dying phase. In fact, Betelgeuse is expected to explode as a supernova in the relatively near future. It could happen anytime in the next 100,000 years, which is a blink of an eye for a star. It might be tomorrow, or it might be far beyond our lifetimes. We can't pinpoint exactly when, but we know the star is nearing the end of its life. When Betelgeuse does explode, it will likely shine as bright as the full moon in our sky for a few weeks and be easily visible even in daytime. What leads a star like Betelgeuse, or any other massive star, to such a violent end? The difference lies in what happens in the star's core after the hydrogen is used up. A high-mass star has the gravity and pressure to push the boundaries of fusion much further than a star like the Sun can. When hydrogen in the core runs out and the core contracts, the temperature soars high enough to ignite the fusion of helium into carbon and oxygen. Once helium in the core is exhausted, the core contracts and heats again, and the star's envelope expands into a red supergiant. But in these behemoths, the core gets hot enough to start fusing carbon into heavier elements. The pattern continues in a kind of fusion cascade. Carbon fuses into neon, magnesium, and sodium. When carbon is depleted, the core contracts and heats, and then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. The star builds up onion like layers of fusion shells. hydrogen burning in an outer shell, helium burning in a shell beneath that, carbon burning in a shell closer in, and so forth, all the way to a growing iron core in the center. The iron core is the final product of fusion, because fusion of iron doesn't release energy, it consumes energy. That's a crucial point. Up until iron, fusion can power the star, but once the core accumulates iron, further fusion would not yield net energy. So, as iron builds up in the core of a massive star, the star is living on borrowed time. The star continues burning elements in shells around the core, piling more and more iron into the center. Meanwhile, the time spent on each successive fuel is shorter and shorter. A massive star might spend millions of years fusing hydrogen, maybe 1 million years fusing helium, but perhaps only a few years fusing carbon, a few months fusing oxygen, and mere days fusing silicon into iron. Eventually, the iron core reaches a critical mass. At that moment, the star can no longer support its own weight. For a massive star, this is the final act, and it's dramatic. When the iron core can no longer hold itself up, it collapses catastrophically under gravity. This collapse happens incredibly fast. In under a second, the core implodes. The temperatures in the core skyrocket, and atomic nuclei get crushed together. Protons and electrons merge into neutrons, so the core essentially becomes one giant atomic nucleus, a ball of neutrons. The collapse is suddenly halted by the degeneracy pressure of neutrons. In that instant, the infalling material rebounds off the stiff neutron core. A powerful shockwave is sent roaring outward through the star's interior. The core collapse and rebound is so intense that it unleashes an enormous burst of neutrinos and a tsunami of energy. The star's outer layers are blown off in one of the most violent events in the universe, a supernova explosion. If the core of the star at the time of collapse is below about 2003 solar masses, it will become a neutron star, the ultra-dense, city-sized stellar remnant, composed almost entirely of neutrons. If the core is above that mass threshold, even the neutrons cannot halt the collapse, and the core will continue collapsing into a black hole, a point of practically infinite density. Either way, the core's collapse triggers the supernova blast. In a supernova, the star's entire outer structure is ripped apart. The star's brightness increases tremendously for a short time. A supernova can briefly outshine an entire galaxy of normal stars. Imagine a single star suddenly shining brighter than 100 billion stars combined. That is what a supernova can do. It will radiate as much energy in a few weeks as the sun will in its entire 10 billion year lifetime. If such an event happens relatively nearby, it can be visible from Earth, even in the daytime. Human astronomers have indeed witnessed supernovas in the past. Historical records from East Asia and the Middle East describe guest stars appearing in the sky. For example, in 1054 AD, Chinese astronomers noted a new star that was visible in daylight for weeks. This was a supernova. Another supernova was observed in 1604. More recently, in 1987, a star exploded in the Large Magellanic Cloud and could be seen by the naked eye. In our own Milky Way, no supernova has been observed in the past 4 centuries, but statistically, we expect a few per century meaning we could be due for another any time in the future. In the chaotic violence of a supernova, there is a remarkable silver lining. This is the event that forges many of the heavy elements that enrich the universe. During the star's normal life, it created elements like carbon, oxygen, and silicon in its core. But elements heavier than iron, such as gold, platinum, and uranium, require the extreme conditions of a supernova to form. In the supernova blast, atomic nuclei slam together in rapid fire reactions, building up many of the heaviest elements on the periodic table. The explosion then scatters these newly forged elements out into space. The stellar ashes, carbon, oxygen, calcium, iron, gold, and so on, are flung far and wide, mixing into the gas between stars. Supernovae are therefore cosmic gardeners, seeding the interstellar medium with the ingredients for future generations of stars and planets. The very material that makes up our Earth and our bodies has gone through this cycle. The iron in your blood, the calcium in your bones, the oxygen that you breathe, those atoms were once created in the interior of a star or in a supernova explosion. As a NASA astrophysics team put it, we truly are made of stardust. The calcium in your teeth, the iron in your hemoglobin, the carbon in your DNA, all were forged in stellar furnaces. Indeed, without the carbon, oxygen, nitrogen, and other elements spread by stars, Earth could not have solid ground, air, or water, and life as we know it would be impossible. We owe our existence to stars that died long before the Earth formed. Indeed, without the heavy elements from stars, there would be no rocky planets, no air or oceans, and no living beings. Meanwhile, what's left of the star's core becomes either a neutron star or a black hole, as mentioned. Neutron stars are fantastical objects. Imagine something more massive than our Sun crushed into a sphere only about 20 kilometers across. They are so dense that a single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The gravity on its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerating to millions of kilometers per hour. Neutron stars often spin rapidly. Some rotate multiple times per second and emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep around like lighthouse beams. If such a beam points toward Earth periodically, we see pulses of radiation. These are observed as pulsars. The first pulsar was discovered in 1967 as a mysterious radio pulse every 1.3 seconds, so regular that the discoverers jokingly nicknamed it LGM-1, half, seriously wondering if it was a signal from an alien civilization. We now know it was a rapidly spinning neutron star. Pulsars can spin unbelievably fast. The fastest known pulsar rotates more than 700 times per second. Imagine an object more massive than the Sun, spinning hundreds of times a second. It defies the imagination. Some neutron stars, called magnetars, have magnetic fields even more extreme, up to 1,000 times stronger than a typical pulsar. A magnetar's field is so extraordinarily powerful that, at a few thousand kilometers away, it could disrupt electronics on Earth. Occasionally, magnetars undergo starquakes that release giant flares of X-rays and gamma rays. If the star's remnant core was too massive to form a stable neutron star, it continues collapsing beyond even the neutron stage. In that case, the core becomes a black hole, an object with gravity so intense that nothing, not even light, can escape from its vicinity. A black hole formed from a single star might contain, say, 5 or 10 solar masses of material, but all of that mass is crushed down into an infinitesimally small volume at the center. The region around it from which not even light can escape is called the event horizon, effectively the point of no return. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers in radius. If the Sun was somehow compressed into a sphere only 6 kilometers across, it would become a black hole. For something as massive as Earth, the event horizon would be barely a centimeter across, meaning Earth would have to be crushed to the size of a marble to turn into a black hole. These numbers illustrate how incredibly dense and compact black holes are, matter and gravity in their most extreme state. Because no light comes from a black hole itself, we cannot see a black hole directly as a glowing object. A lone black hole floating in space would appear truly black, a gravitational trapdoor in the cosmos. However, we can detect black holes by their effects on surrounding matter. Often, a black hole will have gas around it. That gas forms a swirling accretion disk as it spirals into the black hole, and it gets extremely hot, often emitting X-rays that telescopes can detect. We also observe stars orbiting an invisible mass. For example, the center of our Milky Way galaxy has stars whipping around an unseen object, which we know is a supermassive black hole. In recent years, astronomers have even managed to capture direct evidence of black holes by imaging their silhouettes. In 2019, the Event Horizon Telescope project released the first picture of a black hole, or rather, of the glowing gas around a black hole's event horizon. It showed a ring of light and a dark central shadow, exactly as predicted by physics. This was the supermassive black hole in a distant galaxy. And in 2022, we finally saw a similar image of the supermassive black hole at our own galaxy's center. Black holes, once purely theoretical, are now actively studied cosmic phenomena. Amazingly, even after a star has died, its story might not be completely over. Sometimes, the remnants left behind can have dramatic afterlives. For example, if two neutron stars eventually orbit each other, they will gradually spiral inward over time. After millions of years, they may collide in a spectacular event called a kilonova, a merger explosion even more energetic than a typical supernova. Such mergers produce strong bursts of gravitational waves that propagate outward. In 2017, scientists detected gravitational waves from a neutron star collision and also saw a flash of light from it. This was the first time we observed both gravitational waves and electromagnetic radiation from the same event. That neutron star merger forged copious amounts of heavy elements and scattered them into space. Black holes can merge with each other too. When they do, they emit a flood of gravitational waves. We can't see the merger, but detectors on Earth can hear the fabric of space tremble. In 2015, LIGO observed such signals for the first time, confirming a major prediction of Einstein's theories. These phenomena show that even in death, stars can continue to influence their surroundings in extraordinary ways. After a supernova fades, all that remains of the star may be a dense remnant, plus an expanding cloud of gas and dust, the supernova remnant. The ejected material from the star, now racing outward, sweeps up the surrounding interstellar gas and dust, creating a shell or complex filamentary structure that can glow for tens of thousands of years. The Crab Nebula, for instance, is the beautiful filamented remnant of the supernova of 1054 AD, still expanding at thousands of kilometers per second. Over time, these remnants disperse and mix with the interstellar medium. And here, the grand cycle turns anew. The scatterings of old stars eventually become part of new nebulae, providing the enriched raw material for future stars. The next generation of stars will form out of clouds, seeded with the heavy elements of previous generations. Our Sun is thought to be a late generation star, born roughly 4.6 billion years ago from a nebula already seeded with heavy elements by earlier supernovae. Those elements made it into our Earth and into us. We truly are, as the saying goes, children of the stars. Stars, then, are not only beacons of light, but cosmic alchemists and recyclers. Through their life cycles, they transform the primordial hydrogen and helium into a rich array of heavier elements. And through their deaths, they redistribute those elements across space to fertilize new star formation. Generations of stars have built up the carbon in our tissues, the oxygen in the air, the silicon in rocks, and every atom of every element heavier than helium. The universe began with mostly hydrogen and helium, and it is the stars that fashioned all the rest inside their hot cores. It's a magnificent ongoing circle of stellar evolution and renewal, star birth, star life, star death, and new stars born from the remnants. This cycle has been going on for billions of years and will continue for billions more. It is the engine that drives the chemical enrichment and dynamic evolution of galaxies. When we survey the night sky filled with stars, we are gazing at a vast cosmic ecosystem in action. Each pinpoint of light has its own history and future. Some of those stars may be like our sun, gently burning for eons. Others might be giant stars soon to explode, or faint red dwarfs just chugging along. There are hundreds of billions of stars in the Milky Way galaxy alone, and beyond that, billions of other galaxies, each with their own billions of stars. The total number of stars in the observable universe is estimated to be around 10^22. That's a 1 with 22 zeros after it. This number is so huge that it defies true comprehension. One popular comparison is that there are more stars in the universe than grains of sand on all the beaches on Earth. In fact, astronomers estimate there are on the order of 10,000 stars for every grain of sand on Earth. It's an astonishing thought. Next time you're at the beach, pick up a handful of sand and consider that the stars outnumber those tiny grains. Every one of those stars is a sun, and many of those suns have their own families of planets. The universe is teeming with stars beyond counting. Understanding the life cycle of stars gives us a profoundly richer appreciation of the night sky. When you next gaze up at the stars, remember that those twinkling lights are not mere points. They are distant suns, each with a life story spanning eons. The star that looks like a pinprick could be a giant blazing at millions of degrees, or a diminutive red ember glowing softly. Some of the stars you see tonight might already have exploded in the far past, their light only now arriving at Earth after traveling for centuries through space. In a very literal sense, we are connected to these stars. Our planet and our bodies are composed of star-born atoms. Indeed, without the heavy elements forged in stars, Earth wouldn't exist as a rocky world, and human beings could not have come to be. As the late astronomer Carl Sagan famously said, "We are made of star stuff." We are the universe's way of knowing itself, formed from the ashes of long dead stars. In the end, the saga of stars is the saga of the universe. It's a story of creation and transformation on an epic scale, of diffuse gas gathering to ignite nuclear fire, of shining stability and convulsive death, of elements forged in celestial furnaces and cast into the darkness to become the seeds of new worlds. Stars have illuminated the cosmos for over 13 billion years, and they will continue to do so long into the future. Every twinkling star in the sky is a testament to the ongoing cycle of cosmic birth and rebirth. So the next time you find yourself under a starry night, take a moment to ponder the incredible processes happening above you. Those stars are distant suns, forging the stuff of life, exploding and renewing the galaxy. They light up the darkness and spark our imaginations. Theirs is a never-ending story, one of fire and dust, life and death, and renewal. An endless cosmic dance that has shaped our universe and, ultimately, made our own existence possible. And as long as you can see the stars shining overhead, you are witnessing a part of that grand story unfolding, a story that connects us all to the cosmos and to the dazzling stars that fill the sky. The final glow of the previous story fades, but our journey among the stars is far from over. In fact, it's only just beginning. Out in the cosmic dark, countless stars still beckon with new mysteries and deeper roles to explore. We have gazed upon the life cycles of stars, their births in nebulous cradles and their deaths in explosive finales. Yet there is even more to the stellar saga. Now, let us venture further into the galactic tapestry to uncover how stars themselves shape the grand story of the universe. As we continue, imagine drifting back in time to an era before even the first star ignited. In that primordial darkness, over 13 billion years ago, the universe waited for its first light. When the first generation of stars were finally born, they were unlike any that exist today. These population 3 stars, as astronomers call them, were forged from only the simplest elements, the sole ingredients created by the Big Bang. Theory paints them as cosmic titans, perhaps 30 to 300 times the mass of our Sun, and millions of times brighter. Such massive stars would burn their fuel ferociously fast, blazing only a few million years before dying in titanic supernova explosions. Yet in their brief lives, they performed a vital service. Their searing ultraviolet light rayonized the universe's hydrogen, ending the cosmic dark ages nearly a billion years after the Big Bang. In those first brilliant sparks, the universe transitioned from dark and opaque to radiant and transparent, a fundamental turning point in cosmic history. When those primordial stars lived and died, they also created something entirely new: heavy elements. In their hot cores, nuclear fusion began forging elements heavier than helium, carbon, oxygen, silicon, and more. And when the first stars perished as supernovae, they seeded the cosmos with these heavier elements. Before stars, the universe lacked the ingredients for planets or life. After the first stars, space was enriched with the star stuff from which future generations could build. It's awe-inspiring to realize that nearly all the elements in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, were forged in the hearts of stars that lived long ago. Those early explosions scattered the raw materials for new stars, new planets, and eventually us. Little wonder that astronomer Carl Sagan's poetic truth resonates. We are made of star stuff. The universe had to go through the fires of stellar furnaces to fill the periodic table beyond hydrogen and helium. With each generation of stars enriching the cosmic brew, subsequent stars were born with higher metallicity. Thus began an ongoing chemical evolution, each stellar generation shaping the composition of the next, gradually building up the complexity needed for rocky worlds and living beings. In the wake of the first stars, new generations of stars began to form from the ashes. Astronomers classify these stellar populations by their metal content. The ancient stars that followed the primordial ones are dubbed Population 2. They contain only a small trace of heavy elements, just a smattering inherited from those first supernovae. Many Population 2 stars still shine today. They are the oldest stars in galaxies, often found in the halos of galaxies or in ancient globular clusters. In fact, some globular star clusters in our Milky Way are nearly 13 billion years old, almost as old as the universe itself, and their stars preserve a fossil record of the early cosmos. These venerable suns are cosmic time capsules, their faint metal content telling us they formed when the universe was still poor in heavy elements. By contrast, Population Y stars, like our own Sun, are rich in heavier elements. Population I stars are younger, born later in cosmic history, from gas already recycled and enriched by countless prior stellar lives. They reside mostly in galactic disks and include many bright, hot stars, as well as middle-aged stars like the Sun. The distinction between these populations isn't just academic. It's central to understanding how galaxies formed and evolved. In the Milky Way, for example, the spherical halo of old Population 2 stars may be remnants of the galaxy's original build and early mergers, whereas the disk's Population 1 stars reflect ongoing star formation fueled by interstellar gas. The very structure of our galaxy, a thin disk with spiral arms, a central bulge, and a diffuse halo, has been shaped by the continuous birth and death of stars over billions of years. Early in our galaxy's youth, it likely underwent titanic mergers with smaller protogalaxies. One dramatic merger, revealed by the European Gaia spacecraft's star mapping data, occurred around 10 billion years ago when the Milky Way swallowed a dwarf galaxy, now nicknamed Gaia Enceladus, or the Gaia Sausage. This cosmic collision delivered a vast influx of stars into the Milky Way's halo. The evidence is written in the motions and chemical makeup of many halo stars, which are distinct from native Milky Way stars, a sign that they originated in another galaxy. During such mergers, bursts of star formation likely ignited as gas clouds were jolted and compressed. Thus, the Milky Way's early history, the thickening of its disk, the build up of its stellar halo, was driven in part by starbirth sparked in the chaos of mergers. Time and again, galaxies grew by merging and forming new stars, with each generation of stars influencing the galaxy's structure and dynamics. Star formation itself tends to be a self-limiting and self-propagating process. Massive young stars radiate intense light and spew stellar winds, which can carve cavities in the surrounding gas. When the most massive of these stars go supernova, they blast the gas with shockwaves. This feedback can either trigger new stars or quench star formation. In dwarf galaxies, a few vigorous supernovae can blow out much of the gas, stifling further starbirth. In larger galaxies, star formation and supernova feedback regulate each other in a complex dance, ensuring that galaxies don't convert all their gas into stars at once. Indeed, observations show that the universe's star formation rate peaked about 10 to 11 billion years ago and has been declining ever since. At its height, galaxies were forming stars at a frenetic pace, so much so that today's rate is only a few % of that peak. Over billions of years, much of the free gas in galaxies has been used up or locked into stars, and energetic feedback from stars has kept a lot of remaining gas too hot to collapse easily. Our cosmos is slowly simmering down. Still, new stars continue to be born even now, especially in the rich spiral arms of galaxies. In our Milky Way, stellar nurseries like the Orion Nebula are actively turning out fresh stars. But the overall trend is inexorable. The fuel for star formation is finite, and eventually it will run low. Gazing far into the future, astronomers estimate that in roughly 100 trillion years, all the usable star-forming gas will be exhausted or locked up. By that far epoch, the era of star formation will draw to a close. The universe will transition into a quieter stage, dominated by the embers of stellar evolution. Myriad white dwarfs slowly cooling into black dwarfs, neutron stars and black holes lurking in the darkness, and only the occasional new star flickering to life from the rare merger of two old stellar remnants. But fear not. At present, the universe is still richly populated with shining stars, and we live in a cosmos that is very much alive with stellar light. Let's turn our attention to the stars as architects of their galaxies. Every galaxy's visible beauty, its shimmering starlight, its glowing nebulae, comes from stars. Stars delineate the spiral arms of disk galaxies, with luminous young star clusters tracing out spiral patterns like celestial fairground lights. In majestic barred spirals and elegant ellipticals alike, the collective light of billions of stars gives each galaxy its form and color. Hot, young stars glow blue, white, giving star-forming galaxies a bluish hue, while older, cooler populations lend a yellow-red warmth to galaxy bulges and ellipticals. Thus, the mix of stellar ages influences a galaxy's appearance. A young, actively star-forming galaxy looks very different from an old, evolved system, precisely because of its stars. Over cosmic time, galaxies can even change type as their star formation slows. A disk galaxy may fade and redden into something more akin to an elliptical if starbirth ceases and its blue stars die out. The grand narrative of galaxy evolution is intimately tied to the cycles of star formation within. Now consider not just individual stars, but stars in pairs and groups. It may surprise you to learn that most stars in the sky are not solitary like our Sun, but part of binary or multiple star systems. Imagine two stars locked in a gravitational waltz, orbiting a common center of mass. Such binary star systems are incredibly common, by some estimates, more than half of all Sun. Like stars have a stellar companion. In these systems, stars can profoundly affect each other's evolution. Sometimes one star will swell into a red giant and transfer mass to its companion, an event that can spark explosive outbursts or novae. In fact, one type of supernova occurs in an elderly binary. A dense white dwarf star siphons gas from a companion until a runaway explosion is triggered, obliterating the white dwarf. These Type Ia supernovae are immensely important standard candles that have helped astronomers measure cosmic distances and the expansion of the universe. The discovery of the accelerating expansion of the universe, and hence dark energy, hinged on observations of distant Type Ia supernovae. Thus, an intimately interacting binary pair on the stellar scale produces a beacon visible across billions of light years, allowing us to gauge the universe's fate. In other binaries, two massive stars might evolve in tandem and eventually merge or collide. In globular clusters, such stellar collisions can produce the enigmatic blue straggler stars, stars that appear unexpectedly young and blue in a cluster of otherwise old stars. Blue stragglers are thought to form when two stars coalesce into a single, more massive star, effectively rejuvenating it. The result is a star that stands out as bluer and more luminous than it should for the cluster's age, a literal stellar oddball that reveals the cluster's dynamic past. The overcrowded cores of globular clusters facilitate such collisions, offering yet another example of how stellar interactions can yield peculiar outcomes. Some binaries consist of extremely exotic partners, for example, a neutron star or black hole orbiting a normal star. These systems can produce astonishing phenomena like X-ray binaries and even the recently detected gravitational waves. Picture a dense neutron star, essentially a city-sized atomic nucleus with the mass of the Sun, pulling gas off a companion star. As the gas spirals in, it heats up and emits powerful X-rays, making the binary shine brightly in X-ray light. In 1967, astronomers discovered pulsars. The first was affectionately nicknamed LGM-1 for Little Green Men 1, because its precise radio pulses were so mysterious, they were jokingly suspected to be alien signals. Soon, pulsars were understood as rotating neutron stars, the collapsed remnants of supernova explosions. In some binaries, two neutron stars orbit each other, gradually spiraling as they radiate gravitational waves. In 2017, humanity observed for the first time the space-time ripples from such a neutron star merger, along with a dazzling multi-wavelength light show called a kilonova. That single event confirmed that neutron star collisions forge many of the universe's heaviest elements, and demonstrated how closely stellar death and cosmic alchemy are intertwined. Similarly, the first direct detection of gravitational waves in 2015 came from a merger of two stellar mass black holes, remnants of massive stars that had danced together until coalescing. These gravitational wave discoveries opened a whole new window on the universe, essentially hearing the sound of stars merging in the dark. Through binaries and their sometimes violent interactions, stars have enabled us to confirm Einstein's theories, understand extreme states of matter, and even create new fields of astronomy. While many stars live in pairs or clusters, our Sun stands alone. Yet the Sun is no less influential for its solitude. It anchors our solar system, and its steady light allowed life to flourish on at least one world. The Sun's story is still unfolding. About 5 billion years from now, it will swell into a red giant, becoming so large that it engulfs Mercury and Venus, and possibly Earth as well. By then, Earth will be a scorched cinder. As the Sun expands, it will also begin to blow off its outer layers. In its death throes, it may create a beautiful planetary nebula, a glowing shell of expelled gas, before finally settling down as a white dwarf. This stellar remnant, about the size of Earth but containing nearly half the Sun's mass, will slowly cool like a fading ember for trillions of years. That is the long-range fate of our Sun and stars like it. to quietly shed their outer envelopes and leave behind dense cores. The galaxy will become littered with these white dwarfs, cosmic embers that, though faint, carry the memory of their progenitor stars. Even in death, stars continue to shape their surroundings. When a massive star explodes as a supernova, it leaves behind either a neutron star or a black hole. The expanding supernova remnant, a glowing cloud of ejected material E, can crash into surrounding clouds and trigger new rounds of star formation. Think of the Crab Nebula, the remnant of a supernova observed in 1054 AD. At its center lies a whirling pulsar energizing the nebula, and around it, the expanding filaments are rich in elements like oxygen, nitrogen, and iron, synthesized in the star's final moments. Those elements will eventually mix into interstellar space, seeding future molecular clouds. In this way, each supernova is both an ending and a beginning. An ending for a massive star, but a beginning for new stars that will one day condense from the enriched debris. Meanwhile, the neutron star left behind pours out winds of high-energy particles, sculpting and illuminating the nebula. A stellar corpse can thus continue to inject energy into the galaxy's ecosystem long after the star's death. Black holes, too, play a role. If a stellar mass black hole devours gas or stars, it converts that mass to energy, impacting the ambient gas. And on a galactic scale, supermassive black holes lurking in galaxy centers, themselves the end, products of stellar processes and mergers can profoundly influence star formation in their host galaxies by blasting out energy. But those supermassive black holes are a tale for another time. In our story, we focus on the stars themselves, the little black holes they leave behind, and how even those contribute to the cosmic tapestry. Consider for a moment the sheer number of stars out there. Our Milky Way alone holds on the order of 100 to 400 billion stars. It's a figure almost beyond comprehension, and yet the Milky Way is just one of perhaps hundreds of billions of galaxies in the observable universe. If each of those has 100 billion or so stars, you get numbers like 10 more 22 stars in the observable universe. That's a 1 with 22 zeros after it, a quantity of stars truly staggering to contemplate. Each of those stars is a potential sun, perhaps with its own family of planets. In recent decades, we've learned that planets abound around other stars. The once singular idea of another solar system has given way to the realization that planetary systems are commonplace. Using missions like Kepler and TESS, astronomers have detected over 5,000 confirmed exoplanets so far, and counting. Statistics indicate that perhaps 1 in every 5 sun-like stars harbors an Earth-sized planet in its habitable zone. This means when you gaze up at the night sky, statistically the nearest sun-like star with an Earth-ish planet might be only a dozen light years away, practically next door on the cosmic scale. Planetary systems come in a dizzying variety: hot Jupiters, skimming their stars' surfaces, multi-planet systems packed in tight orbits, planets around double stars, and even planets orbiting the crushed remnants of dead stars. There are even planets wandering alone in the dark of interstellar space. Stars and planets are inseparable companions in the cosmic story, and just as stars give birth to planets, planets can influence stars in subtle ways. Take our solar system. The sun's activity and stability have been key to life's development on Earth. Our sun is a rather steady star, but not all stars are so calm. Many young stars and red dwarfs are highly variable and prone to flares. Variable stars in general constitute a broad category, including stars that intrinsically pulsate, erupt, or have eclipsing companions, causing dips in light. These variations have made certain stars vital tools for measuring cosmic distances. For instance, the Cepheid variables, luminous pulsating supergiants, have a well-defined relationship between their pulsation period and true brightness. Discovered by Henrietta Leavitt over a century ago, this relationship allows astronomers to determine a Cepheids' distance by comparing its known true brightness to its observed brightness. Using Cepheids as standard candles, Edwin Hubble measured the distance to the Andromeda Galaxy in the 1920s, discovering that Andromeda lay far outside our Milky Way, thus proving that the universe is populated with myriad galaxies. Later, Cepheids and Type Ia supernovae would help establish that the universe is expanding and, in fact, accelerating in its expansion due to mysterious dark energy. It's poetic that the rhythmic beating of variable stars' light has served as a cosmic yardstick, allowing us to map the universe at large. A throbbing Cepheid in a distant galaxy becomes a beacon, indicating that galaxies' distance, and hence offering insight into the scale of the cosmos. Not all variable stars are so regular and helpful. Some are downright capricious. There are flare stars that can double in brightness in minutes, eruptive variables like young stellar objects that burp out bursts of light as they gulp down fresh gas from their surroundings, and giants like Mira, a star in Cetus that pulsates over many months, varying so much that it can nearly disappear from view and then return. And who could forget the recent drama of Betelgeuse, the red supergiant shoulder of Orion? In late 2019, Betelgeuse dimmed startlingly, losing 2/3 of its brightness, causing speculation that it might be about to explode as a supernova. Observations eventually indicated that Betelgeuse had likely ejected a cloud of dust that temporarily obscured its light from our vantage point. By mid-2020, Betelgeuse returned to normal. This episode was a vivid reminder that stars are dynamic, evolving entities, not static points of light. Betelgeuse is expected to go supernova sometime in the next 100,000 years, a blink of an eye in cosmic terms, and when it does, it will light up our sky brilliantly for weeks, a spectacular final act for a star perhaps 15,020 times the Sun's mass. If we're lucky enough to witness it, that supernova will be a momentous event in human skywatching history. But even short of such cataclysms, the variability of stars teaches us about their inner workings. Through the field of astroseismology, astronomers study tiny pulsations in stars to infer their internal structures, analogous to how geologists use earthquakes to probe Earth's interior. Our Sun, too, has a mild 11th-year cycle of activity, modulating its sunspots and flares, which subtly affects solar output. Thankfully, the Sun's variability is slight. A more erratic star might have made Earth's climate far less stable for life. Stars, then, are creators, testers, and timekeepers of the universe. They create the elements that form planets and people. They test the laws of physics in extreme conditions, from nuclear fusion in cores to relativistic speeds in neutron stars. They serve as timekeepers by revealing cosmic distances and ages through their life stages and variable rhythms. And collectively, stars brighten the universe, turning the primordial darkness into a cosmos of light and color. It is sobering and fascinating to realize that the universe's era of starlight is, in a sense, a finite chapter. We live roughly in the middle of this chapter. For billions of years before stars, the universe was dark, and trillions upon trillions of years in the future, after the last stars have flickered out, the universe will go dark again. But right now, and for many eons to come, it is the age of stars. An age in which galaxies sparkle and life has the opportunity to arise on warm, sunlit worlds. The story of stars is also the story of continuity and renewal. Massive stars live fast and die young, but in doing so, they trigger new growth around them. We see this in regions like the Carina Nebula, where the death of one generation seeds nebulae that birth the next. In a spiral galaxy's life, waves of star formation move through the disk, often stimulated by spiral density waves or past encounters with other galaxies. Our own sun likely formed in a cluster with dozens or hundreds of other stars about 4.6 billion years ago, possibly triggered by a nearby supernova explosion that compressed our natal cloud. Traces of that supernova may be preserved in certain isotopes found in meteorites from the early solar system. Thus, the sun and planets might owe their existence to the death of a long-gone massive star. Indeed, each of us carries the ashes of ancient supernova inside our bodies. The iron in your blood was forged in a star that exploded billions of years before the sun even existed. In a very literal sense, stars are our cosmic ancestors. As we look ahead, what new revelations about stars await us? We stand in an exciting era of astronomy. The James Webb Space Telescope is now peering into the deep cosmos, possibly capturing light from some of the first galaxies and stars that formed over 13 billion years ago. Already, Webb has identified candidate galaxies so far away that they challenge our understanding of how quickly stars and galaxies could have formed. In the coming years, Webb may indirectly detect evidence of population 3 stars, or at least constrain their properties by observing the distant galaxies they inhabit. On the other end of the spectrum, Webb and other observatories are turning their gaze to exoplanet atmospheres, reading the fingerprints of molecules like water vapor, carbon dioxide, and methane as starlight filters through alien skies. In 2022, JWST made the first clear detection of carbon dioxide in an exoplanet's atmosphere, a proof of concept for the detailed atmospheric analysis of potentially habitable worlds in the future. We are learning to read the chemical weather reports on planets dozens of light years away, an astounding development. Future missions will go even further. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys of the Milky Way's center, potentially discovering thousands of new exoplanets through microlensing and mapping out the distribution of stars and dark matter with high precision. The European Extremely Large Telescope, a 39-meter behemoth currently under construction, will in the next decade directly image some exoplanets and dissect the light of stars in distant galaxies, perhaps even detecting biosignature gases on rocky planets around nearby stars. It is mind-boggling. We are on the cusp of potentially finding evidence of life beyond Earth by examining starlight passing through a distant planet's atmosphere. Should we succeed, it would be a profound confirmation that we are not alone, all made possible by the interplay of stars and their planets. Even without finding life, the future of stellar astronomy is bright. New observatories will allow us to watch stars in real time in unprecedented ways, catching the precise moment a star goes supernova in our galaxy, or detecting the subtle vibrations of stars across our galaxy to decode their ages and compositions. We might witness phenomena we've only theorized, perhaps the birth of a black hole accompanied by a flash of neutrinos and gravitational waves, or the mergence of 2 white dwarfs into a new star or a supernova. We may even discover new classes of stars. Who knows? Throughout history, whenever we have opened new eyes on the universe, we've stumbled upon surprises. There could be rare types of stellar objects out there awaiting discovery, stars powered by exotic physics, or stars caught in transitions never before seen. The universe tends to be creative with its use of the physical laws. From the first luminous beacons that banished the cosmic night, to the ordinary middle-aged sun that sustains life on a blue planet, to the spectacular supernovae and gravitational wave chirps that herald stellar deaths, stars have been the main protagonists in the cosmic drama. They are the alchemists that forged the elements, the lighthouses that guide our explorations, and the engines driving the evolution of galaxies. As we float here on our tiny world, bathing in the gentle sunshine of our star, we remain intimately connected to the lives of stars across the universe. Every atom of calcium in your bones was fused in a star that lived long ago and far away. Every gentle sunset tinged with reds and oranges is a reminder that our sun, too, will one day swell and cast a red hue over the sky of whatever beings inhabit Earth in the distant future. Yet even as individual stars perish, the universe ensures the torch of light is passed on. New stars ignite from the ashes, continuing the cycle. And so, the cosmic roles of stars are as profound as they are varied. Stars are creators of light, of elements, of new beginnings. Stars are destroyers. In their violent ends, they can obliterate companions or outshine entire galaxies for a time. Stars are storytellers. Their compositions and motions recount the history of their galaxies. Stars are guideposts. Their steady pulsations and explosions have built our cosmic distance ladder and expanded our knowledge of the universe's expansion. Stars are nurturers, providing warmth and energy to any orbiting planets, and perhaps nurturing life. It is often said that without stars, the universe would have remained a dull, cold fog of hydrogen and helium. There would be no planets, no complex chemistry, and certainly no people to wonder at it all. Indeed, without the stars, the universe would lack its narrative spark. Our exploration of the stars deepens our connection to the cosmos. When we look up on a clear night and see the Milky Way's band of light, we are seeing the integrated glow of billions of distant suns, many of them older, many younger, each on its unique journey from birth to death. Among them are red giants, white dwarfs, neutron stars, perhaps even black holes quietly lurking. All of them together create the shimmering tapestry of the night sky. As we conclude this chapter of the documentary, let's reflect on the awe that stars inspire. For thousands of years, humans have looked to the stars for constancy, for navigation, for myths and meaning. Only in the last century or so have we truly grasped what they are. Nuclear furnaces, balanced by gravity, simple in their basic principles, yet endlessly diverse in their outcomes. And only in the last few decades have we come to see the universe on the largest scales and realize the full extent of the stars' role in shaping everything. The saga of stars is ongoing. Even now, new stars are being born in dusty nebulae. Old stars are blowing themselves apart. Binary stars emerging. Planets are coalescing around nascent suns. Life might be evolving in some distant solar system under the light of an alien star. And photons that left stars billions of years ago are just now reaching Earth, bringing us news from across the universe. With each advance in technology, we become better listeners and observers of the stars' messages. In the near future, we might map the surfaces of stars' light, years away, or detect the faint whispers of stars collapsing into black holes across the universe. And someday, perhaps, we will travel to other stars, our descendants, voyaging across interstellar space to touch those points of light that have beckoned for ages. For now, we continue to study and marvel. The stars have been our beacons, our ancestors, our catalysts. They will continue to shine for billions of years, but not forever. So it is a privilege to exist in this epoch of glittering skies. As our story winds down, step outside on a dark night and look up. Each star you see is part of a grand cosmic ecosystem. Some of those stars are likely orbited by planets you cannot see, perhaps harboring beings who look back at our sun as just another point of light in their sky. In the end, stars connect us across the gulfs of space and time. They are the universals, appearing in the sky of any planet in any galaxy, adhering to the same physics, telling variations of the same tale. This is the cosmic role of the stars, to light up the universe, to forge atoms from the raw stuff of the Big Bang, to sculpt galaxies, to cradle planets, and to continuously renew the cosmos. They are the glittering thread woven through the fabric of space, time, binding the universe together in light. And as long as stars shine, the the universe will not be a lonely, lifeless place, for their light creates the possibility for beauty, complexity, and life. The story of stars is the story of how the universe, once a primordial soup of particles, became self-aware through creatures like us. We are the children of the stars, and through us, the stars know themselves. In the ever-continuing cycle of cosmic evolution, the stars have truly shaped the evolution of the universe, and they will continue to do so far into the future. So, whenever you stargaze, remember, you are watching creation in action, witnessing the ongoing drama that made all of existence possible. The tale of the stars is the tale of us all, a story still unfolding, written across the sky in the light of a billion suns. In the stillness, take a gentle breath. Feel the air quietly enter and leave your lungs. For a moment, nothing exists but this tiny act, a single breath in the dark. You can hear your heart beating, slow and steady. You are in the smallest place imaginable, the space within yourself. A thought flickers across your mind and vanishes. In this hushed, intimate moment, the entire cosmos feels condensed into the rise and fall of your chest. All the rushing world around you has paused. Here is peace, a silent beginning. From that silence, your awareness begins to expand. It's as if your mind's eye opens and starts to float upward. You drift beyond your body, still curled, quiet and warm, and rise softly above it. You sense the room around you, the gentle darkness behind closed eyelids, the floor beneath you, the faint hum of life in the distance. Your breath remains slow, but now you imagine floating higher, passing effortlessly through the ceiling, above the rooftop, above the sleeping earth. The cool night air surrounds you. You can't feel the air, but you know it's there, a thin blanket of atmosphere enveloping everything you've ever known. Rising higher still, you watch the ground fall away. The shapes of houses and trees blur into a dark tapestry. City lights glow in quiet patterns on the land. Further up, those patterns shrink to nothing. Now beneath you is a vast expanse of nighttime earth, silvery moonlight on clouds, a soft halo at the horizon where day is about to break. You are so high that dawn and night share the sky. Above you, the heavens open, countless stars, crisp and bright, scattered across a sea of black. The Milky Way arcs overhead as a faint band of light. For a moment, you hover there, balanced between Earth and space. The world you know is a curved, glowing jewel below, and the universe an infinite mystery above. With a silent urging, you continue upward. The last wisps of atmosphere fade away. The sky goes from midnight blue to pure black. You have slipped free of Earth's cradle and entered the cosmic ocean. Below, the Earth is fully visible now, a luminous blue sphere swirled with white clouds glowing against the dark. Our home. You notice how thin the layer of atmosphere is, just a fragile blue haze along the curved edge. All of life, all of history, contained in that delicate film around the planet. From here, Earth is serene and small, a pale blue dot suspended in an endless void. You feel a quiet awe, realizing that everything you've ever experienced is on that tiny, bright world drifting below you. You drift farther out. Continents and oceans merge into a single marble of blue, white, green, and brown. The bright sun now peaks around the Earth's edge, igniting a halo of light. For a moment, Earth is just a silhouette crowned by dawn. Moving into space's shadow, you see night swallowing half the globe, city lights twinkling on the dark side in silent testimony to humanity. Then even those lights fade. Earth becomes a smaller and smaller circle, shrinking as you float away. Soon, it's just a shimmering dot, like a star. That is home, that tiny point of light, alone in the cosmic dark. Passing the moon's orbit, you look back and see the Earth and moon together. one shining, one softly grey, dancing in eternal circles. The moon, pockmarked and ancient, glows faintly with reflected sunlight. For an instant, you imagine standing on the airless lunar plain, looking up at a blue orb in a black sky. How lovely Earth must appear from there, hanging in space, glowing with life. The thought fades as you journey onward, leaving the moon far behind. The Earth and moon now blend into a single pale star, falling into the background of countless other stars. You carry on, outward and outward, into the deep. The sun looms ahead, no longer a comforting daytime sunbeam, but a blazing white furnace suspended against the void. You feel no heat out here, but you see its brilliant light, a beacon in the darkness. You drift past an inner planet. It's Mercury, a barren, scorched rock, mottled with craters, racing around the sun. Then Venus, cloaked in thick, toxic clouds, gleaming like a pearl. The warmth of the sun diminishes as you go farther, and now the blue-green jewel of Earth is behind you, third planet from the sun, already lost in the sun's glare. Ahead, the rusty world of Mars appears, with its deserts and canyons and faint whiffs of bygone hopes. You glide beyond Mars's orbit, leaving the inner solar system. A cold emptiness envelops you as the sunlight grows weaker, turning golden, then pale. Floating in silence, you pass through the asteroid belt, a vast field of rocks and ice chunks orbiting the sun. They are spread out like dust in a sunbeam. You see only a few asteroids tumble by, ancient and silent. Farther still, the giant planets await. Jupiter materializes, enormous and banded, its great red spot swirling. A centuries-old storm, big enough to swallow Earth. 4 bright moons circle it, miniature worlds in their own right. Volcanic Io, icy Europa, massive Ganymede, cratered Callisto. They glide around Jupiter like a miniature solar system, lit by the distant sun. Next comes Saturn, Lord of the Rings, its golden globe encircled by wide, delicate bands of ice. You marvel at the sheer elegance of those rings, like cosmic artwork carved from light. Titan, Saturn's hazy moon, and a fleet of smaller moons orbit nearby, tiny sparkles moving through Saturn's complex grace. You drift faster now, as if eager to see more. Uranus appears, tipped on its side, a pale cyan orb with faint rings and moons dotting around its tilted equator. Neptune follows, deep blue and mysterious, with winds screaming silently across its methane clouds. Far from the sun now, darkness deepens. The sunlight is just a feeble glimmer, like late twilight on Earth. You pass the orbits of the most distant known worlds and enter the outer realm of the solar system. Here, far beyond Neptune, 1 trillion frozen comets form a tenuous halo called the Oort cloud. These are the ancestral wanderers that sometimes fall sunward and become the glowing comets in our sky. You drift through this cloud of potential, countless icy bodies spread over light years of space, so thinly that you hardly notice when one slips by, a silent snowball waiting for a chance to visit the inner sun. Finally, you reach the edge of the sun's domain. Behind you, the sun is now just another bright star, its family of planets too small to see. In 1977, humanity sent a messenger this far, a Voyager, now over 40 years into its endless journey. It has long crossed the border where the solar wind's breath yields to the breeze of interstellar space. You have followed it into the truly unknown, the space between stars. Here, there is almost nothing, just a few stray atoms per cubic meter, a dusting of cosmic rays, a memory of starlight. The darkness is profound and quiet. Before you, the stars stretch out in every direction. The nearest star to our sun, Proxima Centauri, lies over 4 light years away. So distant that even at the speed of light, the fastest speed there is, it takes over 4 years for a beam to travel from our sun to that star. At your supernatural pace, distance means little, but you recall what this emptiness signifies. The gap between stars is vast beyond imagining. If you were traveling in a ship, moving as fast as any human ever has, it would take tens of thousands of years to reach even the nearest neighboring star. Space is mostly emptiness. You are grateful that as a thought, a consciousness drifting free, you are unbound by such limits. You can roam the interstellar gulf freely, carried only by curiosity. A dim, reddish star comes into view. Proxima, a faint red dwarf, companion to the brighter Alpha Centauri double star system. Perhaps a few small planets cling to it. One, we know, is in a temperate zone, but it is far too faint and distant to reveal itself to our naked eyes. You drift past it swiftly, moving ever outward, picking up speed now. The stars around you begin to form subtle patterns, a hint of structure in the sprinkling of lights. They are no longer random points. You start to notice a concentration of stars in one broad band, the plane of the Milky Way galaxy. From inside, the Milky Way is that cloudy band across our sky. But as you rise above the galactic plane, you begin to comprehend its true form. Pulling farther out, you see our galaxy in full. Behold the Milky Way, a great spiral galaxy, majestic and sprawling, rotating slowly in space. It's like a giant, flat disk of stars with a bright central bulge. Huge, wispy spiral arms unwind from the center, like the arms of a graceful octopus, each arm glittering with millions of stars. Here and there, dark lanes of dust weave through the starlight, obscuring parts of the arms. The disk of the galaxy is over 100,000 light-years across, so wide that even light itself, at its incredible speed, takes 100 millennia to cross from edge to edge. This colossal system holds perhaps 300 billion stars. Amid those, our sun is just one modest yellow star located about halfway out from the center, in a minor spiral arm called the Orion Arm. All around the flat disk swarm countless stars, blue giants, yellow suns, red dwarfs, alongside glowing nebulae where new stars are born and old stars' remnants where they died. Your perspective drifts high above the galactic plane, giving you a view akin to a cosmic vantage point few could ever see. The Milky Way's spiral pattern lies below you now, slowly rotating clockwise. The central bulge is bright and teeming, millions of stars densely packed near the core, orbiting an unseen monster. At the very heart of our galaxy, in that central hub, lurks a supermassive black hole. Invisible against the radiant starlight, it makes itself known through the furious orbits of stars whipping around an empty darkness. This black hole weighs millions of times more than our sun, and its gravity is so intense that not even light can escape once drawn in. Occasionally, a star ventures too close and gets ripped apart, sending flares of X-rays out. But mostly, this dark heart quietly governs the orbits of inner stars. Time and space themselves warp around it. If you could hover just outside its event horizon, the point of no return, time would slow to a crawl for you relative to the outside universe. From far away, you'd appear frozen in place near that abyss. Such is the strange nature of gravity, foretold by Einstein. Where gravity is strongest, time runs slowest. You drift a cautious distance from this central darkness, feeling a reverent respect. In the huge panorama of the galaxy, the black hole is but a pinprick at the center, yet it affects the dance of stars around it profoundly. You leave the galactic center behind and sweep out beyond the Milky Way's disk. The galaxy's full magnificence lies before you, a glowing spiral hovering in space, its starlight diminishing at the edges into faint, tenuous streams. Surrounding the flat disk is a nearly invisible halo of mysterious dark matter, massive yet unseen, extending far beyond the visible galaxy. Though you cannot see it, this dark matter halo is there, holding the galaxy in its gravitational grip. Without it, the stars in the outskirts would fly off into space, unable to be held by the gravity of the visible matter alone. The luminous Milky Way is like a jewel embedded in an enormous hidden cloud of dark matter that outweighs all the stars by 5 times or more. It's a strange thought. Most of the matter of our galaxy is invisible, a transparent ghost shaping the galaxy's fate. But you sense its presence as a gentle tug, a scaffold on which the galaxy is built. Now you look around and realize the Milky Way is not alone. In this vast cosmic neighborhood, it has companions, an island universe among others. Floating relatively nearby is another majestic spiral, Andromeda, our sister galaxy. Andromeda is larger than the Milky Way, a sprawling city of 1 trillion stars, 2 million light years away. It appears as a faint smudge from Earth's skies, but from here, hovering in intergalactic space, you see it face on in all its glory. Spiral arms, bright core, a mirror to our own galaxy's splendor. Andromeda and the Milky Way are falling inexorably toward each other. In several billion years, far beyond any human timescale, these 2 giant galaxies will collide and merge, their stars mingling like grains of sand pouring together. Perhaps they will form a new, larger elliptical galaxy, and the night skies of whatever worlds exist then will be filled with a stunning fireworks of new star formation. But that future cosmic dance is eons away. For now, the galaxies simply drift as silent neighbors. You also notice a collection of smaller, fuzzy patches, dwarf galaxies. The Magellanic Clouds, satellite galaxies of the Milky Way, are there trailing like 2 attendants. Andromeda has its own retinue of dwarf galaxies too. Together, the Milky Way, Andromeda, and about 50 smaller galaxies form a gravitationally bound collection, the local group. You pull back further. The local group, spanning a few million light years, now appears as a tight cluster of galaxies in your view. Andromeda and the Milky Way dominate, 2 spirals swirling amid a crowd of smaller ellipticals and irregulars. As you continue to withdraw, this local group shrinks, merging into a larger pattern. You begin to see dozens, then hundreds of other galaxies glimmering in the void around. They are not uniformly spread. They too cluster in groups and chains. The local group is falling toward a much larger assembly of galaxies, a massive cluster called the Virgo cluster, home to over 1,000 galaxies. You drift in that direction, and soon a spectacular cluster fills your sight. Giant elliptical galaxies, glowing balls of billions of stars, dominate the cluster's core. One of them, M87, harbors another supermassive black hole that astronomers have imaged as a dark shadow against a ring of fire. Spiral galaxies, like whirling pinwheels, are scattered around, and numerous dwarf galaxies pepper the cluster like sparks around a bonfire. Between the galaxies, an incandescent plasma of hot gas glows in X-rays, faintly visible to your mind's eye. This intracluster gas is the sign of the cluster's deep gravity well. It's astonishing. Space can be filled with such richness in one place and such emptiness in another. Up until now, we've journeyed through space, but also, implicitly, through time. Light has a finite speed, so looking far means looking back. Pause here in the heart of the Virgo cluster, about 50 million light-years from Earth. The light reaching you from these cluster galaxies set out 50 million years ago. When that light left, on Earth the age of dinosaurs was ending. In fact, the catastrophic event that wiped them out had just occurred or was imminent. As you marvel at the galaxies, you're gazing into a time when dinosaurs still roamed our planet. Each galaxy carries its history in its light. Your journey continues outward. The Virgo cluster is part of an even larger pattern, an extended structure of galaxies known as the Virgo supercluster, or sometimes Laniakea, our local supercluster. It's a gigantic collection of galaxy groups and clusters spanning hundreds of millions of light years. It's called Laniakea, meaning immeasurable heaven in Hawaiian, an apt name for this monumental system. From your godlike vantage, you see that galaxies are not scattered randomly. They are arranged in vast clusters, strands, and sheets. The Virgo supercluster merges into other superclusters, connected like links in a chain. There are broad patterns emerging, the large-scale structure of the cosmos. You fly further back, and now the grand design fully reveals itself. Galaxies and clusters align like cosmic architecture. Our local group and Virgo cluster are only small pieces of a much larger cosmic tapestry. Imagine a web woven in space-time, delicate yet immense. You are witnessing the cosmic web. Galaxies are the points of light on this web, strung along gossamer threads of matter that span tens, even hundreds of millions of light years. These are the filaments of the cosmic web, the largest structures in existence, thread-like chains of galaxies and galaxy clusters. They intersect in nodes. At those nodes are massive clusters like Virgo, great cities of galaxies where filaments cross. Between the filaments lie enormous voids, empty spaces like vast black holes of nothingness, some hundreds of millions of light years across, with hardly any galaxies inside. The galaxies outline these voids like bright frosting on a dark cake. It's as if the universe has a foamy structure. Imagine soap bubbles clinging together. The galaxies are on the surfaces of the bubbles, and the interiors of bubbles are voids where few galaxies dwell. Most of space, most of the volume of the universe, is nearly empty, the realm of these voids. The luminous galaxies we find are but a thin lattice delineating those huge cavities. You drift along one of these filaments. It's like a luminous river of galaxies flowing through a sea of dark. Each galaxy's combined starlight makes it shine like a tiny lantern, and collectively, a filament can glow faintly across hundreds of millions of light years. Where filaments join, you encounter something even more breathtaking: galactic walls. These are immense sheets or walls of galaxies, where multiple filaments have merged to form structures spanning 1 billion light years or more. One such wall, the Sloan Great Wall, stretches about 1.4 billion light years end to end, so vast that a beam of light, traveling since the time dinosaurs died out, would still be only partway across. And beyond that, an even larger wall has been detected, a structure so colossal it challenges our comprehension, on the order of 10 billion light years in length, nearly the radius of the observable universe itself. Whether it's a single coherent structure or a chance alignment, we don't fully know. But it has been nicknamed the Hercules Corona Borealis Great Wall. If real, it's a concatenation of countless galaxies and clusters, forming a spine across the cosmos. To cross it at light speed would take almost the entire age of the universe. Imagine the immensity, a wall of galaxies, billions of light years long. Here, the cosmic web is at its grandest scale, the largest pattern in nature, a web with threads and knots spanning unimaginable distances. Hovering amidst this cosmic web, you feel a strange sensation. There is an overwhelming grandeur to it, yet an eerie stillness. The galaxies are separated by such vast gulfs that each one seems isolated, yet here you see them as pieces of one colossal structure, like single cells in the body of the universe. And underlying this web is something even more mysterious, an invisible foundation. Earlier, around the Milky Way, you sensed the presence of dark matter. Here, at the scale of the cosmic web, dark matter's role is unmistakable. These immense filaments and walls exist because dark matter's gravity drew matter into these shapes. Long ago, the universe was almost uniform, but not perfectly so. Tiny quantum fluctuations in the very early cosmos, subtle differences in density, no more than a grain more here, a grain less there, were amplified by gravity over billions of years. The regions slightly denser pulled in more matter, growing denser still, while adjacent regions gave up matter and became emptier. Through this relentless, patient process, matter collected into filaments and clusters and left behind voids. Dark matter was the key player because it does not interact with light or heat. It started clumping even when the normal matter was still a hot, ionized fog. Dark matter formed a kind of scaffolding, a hidden cosmic framework. Ordinary matter, gas and dust, then fell into the gravitational wells of that framework. Dark matter sculpted the cosmic web, and the galaxies lit up along those hidden contours. As you gaze at the cosmic web, you are actually seeing the otherwise invisible dark matter's imprint. Every galaxy is sitting in the cradle of a dark matter halo. Where you find a cluster or filament of galaxies, there lies an even larger clump of dark matter holding them together. And where you find a void, dark matter has evacuated too, leaving a truly empty expanse. Most of the mass of the universe is this dark matter, unseen yet gravitationally potent. It's humbling to realize that everything we see, all the stars and galaxies, is just the glitter on an enormous dark stage. You move through a vast void now, leaving a filament behind. Suddenly, nothing visible surrounds you, an absence of galaxies, like drifting through a huge cosmic desert. These voids are not completely empty. There may be a few stray galaxies or hydrogen atoms floating here, but compared to the bustling clusters, they are almost pure nothingness. One famous void, the Oddities void, is so large and empty that an entire cluster of galaxies the size of Virgo could fit inside it with room to spare, yet it contains almost no galaxies. If Earth were near the center of such a void, we would have discovered other galaxies only in the last century or two, because nearly all would lie beyond our visibility, until powerful telescopes were invented. In this void, the silence is palpable. It's the silence of an empty universe. No stars, no galaxies for tens of millions of light years in every direction. You might feel a chill of loneliness here, but also a sense of profound peace. This darkness is part of the universe's tapestry too. Without voids, the cosmic web would not have its striking contrast and shape. The voids are like the black backdrop that makes the galaxies shine all the brighter. After crossing the void, another filament's glow appears, and you float toward a rich intersection, a supercluster far from our own. Galaxies cluster here in the hundreds, swirling around a common center of gravity. Giant ellipticals dominate, likely formed from earlier mergers of spirals. Clusters of galaxies are entangled in a gravitational dance, slowly converging over eons. You sense the presence of an enormous gravitational anomaly, perhaps the so-called Great Attractor, a region in the direction of the constellation Centaurus that tugs on our local supercluster itself. These massive structures tug on each other, distort the motions of galaxies on even larger scales. The cosmic web is not static. It sways and shivers in slow motion. Over billions of years, clusters merge, filaments stretch, voids expand. Expand. That word reminds you, the universe itself is expanding. All around, on the largest scales, space is stretching. The galaxies recede from one another, like dots on an inflating balloon. Even as gravity pulls local structures together, the overall fabric of space expands relentlessly. You begin to notice something about the most distant galaxies in your view. Their light looks reddened. The gorgeous spiral that should have gleamed white-blue now appears tinted in soft orange-red. This is not because of dust or age, but because the very space between you and that galaxy has expanded during the light's long journey, stretching the light's wavelength. This is cosmological redshift. The farther a galaxy, the faster it recedes, and the more its outgoing light is stretched into longer, redder wavelengths. To your eyes, if you could see these distant galaxies up close, they might be brilliant with young stars, but by the time their light reaches you, perhaps tens of billions of years later, that light has been transformed into a faded echo of what it once was. It's as if the universe's expansion is a gentle, inexorable sigh, draining a bit of energy from each photon that crosses the cosmos. Expansion is not just carrying galaxies apart, it's accelerating. You recall that, a few billion years ago, the expansion of the universe started speeding up, propelled by a strange unknown force. We call it dark energy, not because it's dark like matter, but because it's mysterious. Dark energy seems to be a property of space itself, a sort of built-in pressure or tension that pushes space to expand more and more. In the past, gravity slowed the expansion as galaxies pulled on each other. But as the universe grew emptier and the galaxies got farther apart, this repulsive dark energy came to dominate, and now it drives galaxies away from each other at ever-increasing speeds. You cannot see dark energy, yet you observe its effect. The distances between far-flung galaxy clusters increase faster and faster. Over the next several billion years, this expansion will widen the voids, push clusters further apart, and isolate galaxies from each other's view. One day, in the far future, a lone astronomer in our galaxy, or its merged descendant, might look out and see only darkness beyond the local group, all other galaxies having slipped beyond the horizon of visibility. But that fate lies far ahead. For now, dark energy's influence is subtle in your journey. A slight stretching of the views, a little extra red in the far galaxy's light. Yet it's pervasive, a reminder that the cosmos is dynamic on the grandest scale. As you venture even farther, you approach the edge of the observable universe. This isn't an edge in space where you hit a wall, it's an edge in time. The farther out you go, the further back in time you peer, because that light has taken so long to reach you. At last, you arrive at a point where the first galaxies are coming into view. Tiny proto-galaxies, clumps of stars just forming. Their light is extremely faint and heavily redshifted, some of it stretched right out of the visible range into infrared and radio. These embryonic galaxies appear as small, dim patches. You are seeing them as they were over 13 billion years ago, when the universe was in its infancy. These early galaxies are nothing like the grand spirals and ellipticals you saw earlier. They are smaller, more irregular, often colliding and merging. This is the epoch of galaxy formation, chaotic and creative. Massive stars in these early galaxies burn hot and blue and live short lives, detonating as supernovae that forge heavier elements for the first time. You are glimpsing the cosmic dawn, the time when the universe first began to shine with starlight after ages of darkness. One striking thing here: the space between these primordial galaxies isn't as clear as it was closer to home. There's a haze, a fog of hydrogen gas that is only now being ionized by the brilliant newborn stars and the first quasars, galaxies with actively feeding black holes that blaze like beacons. You've entered an era shortly after the cosmic dark ages. Let's recount. After the Big Bang, once the universe cooled enough for atoms to form, the light from that early fireball could travel freely. That became the cosmic microwave background. But soon after, with no stars yet born, the universe went dark. There were no light sources, just neutral hydrogen gas pervading space. For tens of millions, then hundreds of millions of years, the universe was dark, matter pooling slowly into the first stars and galaxies. Then, perhaps around 200 million years after the beginning, the first stars ignited. Imagine that moment. For the first time since creation, darkness was pierced by starlight. Those first stars were likely gigantic, much more massive than our sun, burning hot and dying young in spectacular supernovae. They emitted intense ultraviolet light that began to re-ionize the hydrogen around them, tearing electrons off atoms and turning the gas back into plasma. As more stars and galaxies formed, this process continued like widening bubbles of clarity in a fog until the fog was fully burned away. This is the epoch you're witnessing, reionization, when the cosmic fog is lifting. It's a patchy, active period. Everywhere, infant galaxies and star clusters are switching on, lighting up pockets of space, their radiation carving out cavities in the hydrogen mist. Over a few 100 million years, these cavities merged and the haze vanished, leaving the transparent universe we know. Moving still further out and back in time, you reach a point beyond which there were no stars at all yet. Only the afterglow of the Big Bang itself fills space. You are now at the edge of the observable universe, about 13.8 billion light-years from where Earth would be, though Earth doesn't exist yet in this time frame. All around you glows a faint light, not from stars or galaxies, but a ubiquitous background. It's the color of warmth, a dim microwave glow invisible to human eyes but detectable with special instruments. This is the cosmic microwave background radiation, the oldest light in the universe that we can ever see. It's a relic from when the universe was only 380,000 years old, long before the first star, long before galaxies, when everything was an incredibly hot, dense plasma of electrons, protons, and photons. At that young age, the universe cooled just enough for electrons and protons to combine into hydrogen atoms. In an instant, the opaque fog of plasma became transparent gas, and light was free to travel. The glow we see is the afterglow of the Big Bang. Back then, it was as bright and hot as the surface of a star, around 3,000 degrees Kelvin, glowing orange-white. But in the billions of years since, the expansion of space has stretched that light to microwave lengths and cooled it to just 2.7 degrees above absolute zero. Extremely cold. Now, it is a faint, uniform whisper of microwave energy everywhere you look. If you've ever seen static on an old television tuned between channels, a fraction of that snow was caused by this primal light still arriving on Earth. Here, on the edge of the observable universe, that gentle glow is all around, like being inside a diffuse, featureless cloud of light. But it's not entirely featureless. If you look closely, you might see tiny variations, 1 part in 100,000, slight warmer and cooler spots. Those are the seeds, the very quantum fluctuations that grew into the cosmic web. In this baby picture of the universe, those warmer spots are a hair denser, the cooler a hair less dense. With time and gravity's help, the dense spots grew into galaxies and clusters. The voids grew out of the less dense spots. It's astounding to think the entire vast cosmic structure you traveled through was encoded in these faint blotches of the cosmic microwave background.
You linger here, at what feels like the limit of existence that we can perceive. This light, the microwave background, is like a wall of light enclosing our vision. It is often called the last scattering surface, because it's effectively the furthest surface from which photons could freely travel to us. Beyond it, farther back in time, the universe was opaque, a brilliant fireball of matter and energy where light was trapped. We cannot see beyond this surface with light. It's the flash of creation's afterglow. But our imagination can venture one step further. We contemplate the Big Bang itself.
Just beyond that curtain of light lies an almost unimaginable state, the universe, newborn, hot, dense, almost uniform, and extremely small. It wasn't an explosion in space, it was an explosion of space. Space and time themselves began their grand expansion here. In your mind's eye, you try to picture it. Some 13.8 billion years ago, everything, all that would become galaxies, stars, planets, people, was compressed in a volume smaller than a grain of sand, at temperatures of trillions of degrees. It is nearly impossible to fathom. But from that state, space erupted outward. The universe expanded at a phenomenal rate. There's the idea of cosmic inflation, a burst in which the universe swelled exponentially fast in a fraction of a second, smoothing and flattening space. Whether you can sense that or not, you feel that suddenly this tiny, hot universe grew and cooled. In mere minutes, it went from nothing to something the size of a grapefruit, then to the size of the solar system, and kept growing. The hot plasma formed basic atomic nuclei, hydrogen and helium mostly, in the first 3 minutes. Then expansion continued more slowly for hundreds of thousands of years as the fireball gradually dimmed and cooled. At 380,000 years, electrons joined those nuclei to form the first atoms, and the blinding opaque glow turned into the transparent universe and left behind the background light we just saw. Then darkness fell, and the stage was set for the first stars. The universe is remembering this early era in every bit of its structure. The cosmic web we saw, that intricate pattern, is like the universe recalling the quantum fluctuations and inflation that set it up. Space itself has memory, written in light and gravity. You listen to that memory, a deep silence with a subtle crackle of ancient light, like an old record playing the sound of creation. Now, as gently as it expanded, your awareness begins its journey homeward. You turn back toward the present, toward familiar shores. Slowly, you drift forward in time. You watch those primordial galaxies cluster and merge. You see the cosmic web sharpen as gravity draws filaments together and voids grow emptier. Time flows faster in your perception now. Hundreds of millions of years flicker by like moments. Galaxies take shape, merging, spinning, evolving. By a few billion years after the Big Bang, grand spiral and elliptical galaxies have formed. The universe lights up with quasars in the hearts of young galaxies, then calms as black holes settle and star formation ebbs to steadier rates. Clusters assemble, superclusters emerge. You witness the birth of our own galaxy. Tiny proto-galaxies coming together, stars forming, dying, enriching gas with heavy elements, new stars forming from that enriched material, generation upon generation. You see our Milky Way grow to maturity, developing its graceful spiral arms. In one of those arms, about 5 billion years ago, you notice a certain giant molecular cloud contracting, an unremarkable event among countless others. But to us, it's special. That cloud will become our solar system. You zoom in as this cloud spins and flattens into a disk. At the center, a protostar ignites, our infant sun. In the surrounding disk, dust grains stick together, building pebbles, then rocks, then planetesimals. Over tens of millions of years, these clump into planets. You see a small rocky planet coalesce in the warm zone third from the sun. Earth is being born, red hot and molten from collisions. Farther out, gas giants gather, and comets dance at the fringes. A Mars-sized body strikes the young Earth, a cataclysmic impact that melts it entirely and throws up debris that coalesces into our moon. Earth's turbulent youth eventually cools. Water arrives, maybe from comets or outgassed from its interior, raining down to form oceans. The sky's clear. The sun shines warmly on a water-rich world. In some tiny, obscure tidal pool or deep-sea vent, around 4 billion years ago, life sparks. Simple and single-celled at first. Your cosmic journey has telescoped down to the micro now, and you find yourself marveling not at galaxies, but at cells. They grow, evolve, photosynthesizing bacteria give off oxygen, transforming the atmosphere. Eons pass. Life grows more complex. By 600 million years ago, multicellular life blooms in the seas. 400 million years ago, plants and creatures venture onto land. 250 million years ago, mighty reptiles rule the earth. 65 million years ago, a rock from space resets the stage, and tiny mammals begin their rise. The stage shifts rapidly now. Apes stand upright on the African savanna, their curious eyes now looking up at the same stars you traveled among. They wonder, they tell stories, they reach for meaning. And here you are, a descendant of those early humans, existing for just a blink in cosmic time, yet able to retrace this entire journey through imagination and science. We return fully to the present, finding ourselves hovering above that familiar blue planet, Earth, now alive with forests and oceans and cities alight in the night. We have come full circle, from the threshold of the cosmos, back to the world we call home. Gently, you descend back toward Earth. The blue dot grows larger, resolving into the globe, then into the shapes of continents and clouds. You slip into the atmosphere like a falling leaf. The ground comes up to meet you softly, and you find yourself back in the stillness of the place you began, perhaps the very room where your body sits or lies in quiet. Rejoin your body. Feel the weight of yourself against the floor or chair. Feel the cool air on your skin. Hear once more the steady rhythm of your breathing, the faint thump of your heart. You become aware that within you, mirroring the cosmos without, there is a universe of atoms and molecules. The journey outward has ended, and now the journey inward begins in reflection. You consider your hand, resting calmly. It's made of trillions of cells, each a tiny city of molecules working together, each molecule built of atoms that were forged long ago in stars. The calcium in your bones was cooked in the heart of a star that lived and died before the Earth was born. The iron flowing in your blood was formed in a supernova explosion, the death cry of a massive star, many billions of years ago, far across the galaxy. The oxygen you inhale with each breath, the carbon that forms your DNA, the nitrogen in your muscles, those elements were minted in nuclear furnaces or when stars perished in tremendous blasts. You are literally made of stardust. The universe made you from its history. You are a composite of ancient atoms, from the Big Bang's hydrogen to heavy metals from generations of stars. Even the empty space inside your atoms, and there is a lot of emptiness, as electrons swarm around comparatively tiny nuclei, echoes the vast emptiness between stars. If you could enlarge an atom to the size of a cathedral, its nucleus would be a mere grain of sand at the center, and the electrons like motes of dust buzzing at the edges. The rest is empty void. You, like the cosmos, are mostly space by volume, punctuated by tiny, energetic particles and forces. We carry within us a structure reminiscent of the cosmic structure, nucleus, like a star, with electrons, tiny planets, bound by electric forces, gravity's analog at microscopic scale. It's not a perfect analogy. Quantum reality is different. But in a poetic sense, we each contain miniature solar systems of possibility. Sitting here, you realize connection. The boundary between you and universe blurs. The cosmos is within us, as much as we are within the cosmos. Every atom in your body has existed for billions of years, cycling through various forms, born in the hearts of stars, dispersed in nebulae, incorporated into new star systems, drifting through space, eventually finding its way to Earth and into the living web of this planet, into the food you eat, the air you breathe, becoming you for a time. And when you are gone, those atoms will return to the Earth, the air, perhaps to new life, and someday, far in the future, may be launched into space again when the sun swells into a red giant and sheds its outer layers, taking your atoms back into the cosmos to rejoin the stars. We are not observers separate from this universe. We are active participants, made of its very substance and sharing its fate. Think of this. The universe has known itself through you. Over billions of years, it developed eyes to see and minds to comprehend. And those are our eyes, our minds. When you stargaze, the universe is looking back at itself. The photons that have traveled for eons enter your eyes and trigger thoughts in your brain, itself a network of atoms that were forged in stars. In a sense, the cosmos has awakened through conscious beings. We are a way for the universe to know itself, to marvel at its own grandeur. Your very awareness is as much a cosmic phenomenon as the gravity that binds galaxies or the light from the first stars. You are the cosmos, in human form, marveling at itself. Now you take another deep breath, as you did at the beginning. Feel your chest rise and fall. Feel how your body is anchored on Earth by gravity, that same gravity that holds planets in orbit and molds galaxies. There is comfort in that familiarity. The vast journey you took, from your body to the edge of the universe and back, might leave you with a sense of wonder, perhaps a touch of melancholy at our smallness, but also, hopefully, a profound sense of belonging. You belong here. The hydrogen in your body was born at the beginning of time. The calcium in your teeth, the iron in your blood, the carbon in your brain, all were brewed in ancient stars long dead, then recycled into new star systems, one of which became our solar system, our Earth, and eventually, you. You are a child of galaxies. You carry the heritage of the Big Bang and the stars in every cell. Think of all the boundaries we set between self and world, between nations, between species, and realize that on a cosmic scale, those boundaries fade. We all share the same origin. Every person, every creature, every rock and river, every atom of Earth, all were together in that incandescent singularity at the dawn of time. We all are siblings in the particle sense. When you look into another's eyes, you see the universe, just as when you look up at the Milky Way. A gentle breeze might blow outside your window. Perhaps a distant car passes. A dog barks. Normalcy surrounds you. Yet, within that normalcy is the extraordinary fact that you are part of something vast and ancient. In a quiet, almost paradoxical way, as you sit here, you contain the whole of existence because you are made of it, because you came from it, and because your mind can encompass it. The atoms in your heart and the atoms in the farthest galaxy, they are different in location but identical in nature, and they obey the same laws of physics, were born in the same cosmic processes. Slowly, you open your eyes, if they were closed. Look around the room or space you are in. It might seem ordinary, perhaps dimly lit, perhaps cluttered, perhaps serene. But notice, the light allowing you to see is a tiny slice of the electromagnetic spectrum that permeates the universe. The chair or floor supporting you is made of matter that was forged in starfire. The very air you breathe connects you to all life on Earth and to ancient stars that blew apart to seed this planet. Our journey ends where it began, with you, here and now, breathing quietly. But you carry with you the resonance of the voyage. In your mind's eye, you can still picture the spiral arms of the Milky Way, the filaments of the cosmic web, the dim glow of the cosmic microwave background. Those images are a part of you now, and whenever you feel lonely or insignificant, remember this feeling. You are inseparable from the universe. You are made of its oldest atoms. You are sustained every moment by its physical laws. You are woven into the same fabric as every shining star and every yawning void. The gravity that holds distant galaxies in clusters is at this moment holding you to Earth and holding the atoms of your body together. The light that left a quasar billions of years ago, showing us the early universe, is the same kind of light that gently warms your skin on a sunny day. We set out seeking the cosmos, and we found ourselves. We imagined going outward to the greatest expanses, and it brought us inward to the smallest corners of our being. In truth, there is no real separation. It's all one continuous reality, from the quantum foam to the cosmic web. As above, so below, the ancient saying goes. The macrocosm reflects the microcosm. Here, at the end of our journey, sit for a moment in that understanding. Feel the quiet awe inside you. You have journeyed from a breath to the edge of time and space and back again. Let a sense of belonging and peace settle in your heart. The cosmos is vast beyond words, and it is violent and beautiful and mysterious. But it is also home. In all its enormity, it has nurtured the pathways for particles to become people who can love and dream. You are a product of this universe, as dear to it as a child to a parent, made of its substance, playing your part in its story. Above you, the stars will continue to wheel in the night sky, distant suns on their own journeys. The earth will spin, bringing dawn and dusk. Generations of humans will be born, look with wonder at the stars, and eventually return to the universe, the substance that was on loan to them for life. Perhaps one day, humans or our descendants will travel to some of those distant stars for real, extending life's reach across the galaxy. But no matter how far we go, we'll only find more of ourselves, because we are the universe exploring itself. Take one more deep breath. Inhale deeply and exhale. Feel the solidity of the ground, the pull of gravity anchoring you, the air filling your lungs with oxygen that trees made from sunlight, the quiet beating of a heart that echoes the first drumbeats of matter so long ago. When you're ready, gently return your focus fully to the here and now. Though our narrated journey is ending, the real journey, your life, on this earth, under these stars, continues. Carry this feeling of cosmic unity with you. In moments of stress or pettiness, recall how precious and unlikely it is to be here at all, a self-aware part of an ancient, magnificent universe. Let it give you perspective and solace. Above all, remember that awe you feel, that quiet, humbling sense of the sublime. The cosmos is vast beyond comprehension, and you are an infinitesimal speck, yet you are also a cosmic miracle, a part of all of this. You belong in this story. The hydrogen in your body, the stardust in your bones, the spark of thought in your mind, all of it is the universe, and it all belongs. In the grand, expanding vastness, in the still center of your own heart, feel the connection. Feel the kinship with everything that is. The cosmos is not cold and alien. It is inextricably linked to you. You are a child of the stars, an heir to the galaxies, and a partner to the universe's endless change. In this union of inner and outer, in this melding of self and all, there is a profound peace. You are home.